Welcome back to day 2 of the GMTSAR short course at UNAVCO. And so today we're getting into more of the details on processing. And this is a really good point. You should ask questions. You can either put the questions in the chat. I've been watching the chat, not so much the Slack, or wait till the end of the presentation and ask questions. But really, there's a lot of details here, and you've got the experts that know the details, and there's a lot of things we could miss. So feel free to ask questions. So we're going to start off with Catherine Materna, and she's going to walk us through one of these 2-pass processing examples and look at the files and try to explain what they are. But again, there's a lot of files, and so I'll be watching the chat. So take it away, Catherine, if you. That looks pretty good.
You probably need to unmute yourself. Yeah.
Okay, can you guys hear me?
Yeah.
Yes.
Sorry about that. All right, so this morning I will share with you guys an example of a Sentinel-1 interferogram across 3 swaths done using the P2P script. This follows very closely the Nicaragua example. This readme.txt is actually the exact readme.txt here that comes from the Nicaragua example. And as Xiaohua mentioned yesterday, the driver of this kind of script is one of these scripts, P2P S1 tops that comes with GMTSAR. And then the main parameters that you guys will start to use in your own processing include the name of the files with the data themselves, the names of orbits that are corresponding. In the case of Sentinel, the name of the second file that's being used and its corresponding orbit, and then this file here, config.s1a.txt. I'll go through some of these, so some of what's in config, and I'll go through some of the files that are produced. Please ask questions, but I don't have access to the, I'm not gonna have the Slack open right now. I'll maybe rely on others to see what some of those questions are. So first I'll start with the organization structure, the directory structure. So you kind of start with a directory called raw, where the data from Sentinel-1 lives, the corresponding orbits. And you start with a directory called topo that has your DEM. The directory raw, you can see these have, generally we don't go into these files, into these safe folders, but they have a lot of things inside them. And for a Sentinel-1 image with 3 subswaths, this thing might be about 3.5 gigabytes. And then this is a text file that shows the orbit. Upon running this P2P script, it will perform several steps in sequence, as Xiaohua mentioned, and you can see them at the top of the config. This is the config file that you pass in, and here are these all-important steps, processing stage, from pre-processing and alignment to resampling the topography, putting it in the geometry. Step 4 is making interferograms, step 5 is unwrapping, and step 6 is geocoding. So in this config file, you can kind of control what you want the program to do. In this case, processing stage starts from 1 and runs all the way through. But at different times, you might want to, start at 4 or do something else. When you run this script, it will start to create these directories. So you can see here, F2, F3, these are the subswaths in Sentinel. And inside is a directory structure that is kind of matching, or it looks very mirror-like of the top directory structure. It has another directory called raw. It has SLC. This is where the images are aligned with each other, and so you'll end up with these are generally pretty large. If I'm not, this is a happens to be a pointer, but the SLCs are large. This is what everyone wants to know about. What is in the interferogram folder? And so you can see the dates of these two images. And inside the interferogram folder is lots of stuff. These LED and SLC, these are symbolic links. So these are just aliases to files that are somewhere else. And then you have a bunch of grid files that GMT is using to compute the correlation and the phase in GMTSAR. And then you have phase fills, phase fillt. Then you have versions of it that say _LL. Those are geocoded. That comes from step 6. So these are in the latitude and longitude coordinates. You have the filtered version of all of these, and you have masked for, I think this is masked based on coherence. And then some of the products of GMTSAR, in addition to these GRD files, GMTSAR also produces images of what it's just done in the form of PNGs, which you can see here for the amplitude, the correlation, the phase, which is masked in this case, the filtered phase. So you see there's a little bit of a difference between what you see if I'm flipping back and forth between phase and phase filtered. And then it produces postscripts of all of these. So you can see in radar coordinates, are range and azimuth in the radar coordinates. And it produces KMLs, which are actually going to read the PNG, plot them onto the latitude and longitude of Google Earth. So as an example, here's all 3 of these subswaths opened up in Google Earth for you. And this is an example from the Kaikoura earthquake in 2016. A magnitude 7.8 earthquake. You can see a lot of fringes in the in Sentinel-1, which is C-band. We also have, so these are some of the output products after computing. So GMTSAR will compute F1, it will compute an interferogram for the first subswath. It will then compute F2, and depending on the mode in which you run it, it may do these in parallel, or F3. And so each of these will look very similar. There's, we'll have these subdirectories with the same structure, and the interferogram folder with the same types of files, the grid files with the data themselves, the PNGs and postscripts for your and KMLs. So all of them will be out in the interferogram directory. And then it will also produce kind of a very similar looking output file or output directory with similar files that are merged. So it will basically put these into one GRD file for you. We can look a little bit into the config file itself. This is very information heavy. There's a lot going on. But I encourage all of you to read the parameters that you can play with in the config file. A lot of them by default, some of these cells are left open because we're using the default values for starters. But some things you can do for parameter for aligning, you can do region cut. Here are parameter, in general, the parameters kind of follow, they go in these headings, and they kind of follow the number of, so the first few parameters kind of match with step 1, and then parameters that match with step 2, and moving to the steps 4, 5, and 6, where we do a lot of the tweaking that comes with making interferograms. You can find here parameters for making and filtering interferograms. A number of parameters that you might actually adjust throughout your processing. One of them is the filter wavelength. 200 meters is default. You can put other values. These parameters here have to do with the decimation in range and azimuth. So this will control the ultimate file size of the interferograms that you produce. These are some new parameters, but in the example that I downloaded, correcting ionosphere is set to false. So we're not doing ionosphere correction. In unwrapping, in this case, there's a parameter called threshold snafu. Snafu is the unwrapping software, and it's separate from GMTSAR, but GMTSAR uses it. Threshold snafu, setting it to 0 means that we're skipping unwrapping. So in this case, we're not unwrapping. But in general, if this is not 0, it's the correlation threshold that is used for pixels with correlation above that value are going to be unwrapped. And then similarly, there's a correlation threshold for pixels that are going to be geocoded. And you can set to 0 to skip geocoding. So these are the final stages to see outputs that you might be interested in. I think that was super fast, super speedy overview. I know there are a lot of questions. I think I want us to pause here and answer questions.
Yes, there are lots of questions in the chat. Let me scroll back a little bit and anyone can answer. So for example, one of the first questions was where to find the P2P processing.csh script. And that should be installed when you install GMTSAR. So if you have your path set correctly and you type that command, it'll tell you how to use it. And there's one for tops. The next question was, well, that was the answer. Jawa gave an answer for tops frame.
In terms of finding the script, a lot of the processing that I've done started by some of the examples. So I downloaded an example and saw the way that it was constructing a call to this, to this exact script, and then kind of developed my own examples off of it.
Yeah, that's the way I always do it too. And someone asked about the F1, F2, F3. Well, if you process just regular strip mode SAR like NVSAT or ERS, you don't have F1, F2, F3. You just have a single swath. But the Sentinel has 3 subswaths and the ALOS 2 has 5 subswaths, and they get processed independently. And then the last step is to merge them all together to make a single interferogram and single correlation. And I don't know what else gets merged. What's in that merge directory? I guess you went through.
It's whatever is used for doing phase unwrapping, the mass, coherence, and phase field, actually.
Phase fields.
So the unwrapping gets done there. Yeah. And then to make KML file, you can make KML files with GMT, but you need to have Google Earth installed to be able to use them.
Yeah, and the trick with the KML files, the thing that's kind of nice about them is If you look at them here, it's very small. It's 600 bytes because it's actually just a text file that says, grab me the PNG and plop it onto the ground in these coordinates. So that means if you're transferring the KML file to another computer, you're sending it to your collaborator, you need to send the PNG along with it. Otherwise it won't work, because these two files are essentially pointing to each other. This PNG is the one that gets displayed on Earth using the KML to do the formatting.
Oh, I see questions. Oh, I'm not scrolling down far enough. Ah. Let's see. Is there a multi-looking parameter? I think we're going to hear about filtering in a minute, but multi-looking is essentially taking pixels in a square box and averaging them, say a 3x3 box, and then averaging them and make one output pixel. But in GMTSAR, it uses a filter, and it has the shape of a Gaussian rather than a boxcar. So we don't call it multi-looking, but it's in there. And then the decimation was in that config file. But if you design a filter that's, say, 500 meters, 500 meters means the, if you looked at the power spectrum, it would be the point where it's 0.5 half filtered. And if you put a 500 meter filter then in, it's going to downsample your image by more than, say, a 200 meter filter. It's automatic, I think. But as you showed, Catherine, in your config file, for Sentinel-1, you sometimes have to force the decimations to be the same in all the three subswaths. So when you merge them, they can merge together. So Sentinel-1 is a little different. Maybe Jawa has some ideas.
Yeah, the main reason that you had to force that is mainly because each of the subswaths are actually processed individually and then merged together later on. If you just allow the program to compute a decimation for you, it might be different for each of the subswaths because the range pixel size changes with range. The far range will have a smaller size and near range have a larger size. That's the main reason that you had to force it to a specific number, say like 8 in range and 2 in azimuth, and then later on the merging could be done properly.
So I see another question here from Rui. What's the best geocode correlation threshold value? And I sort of pick a value that works and gives you output that's sensible, but maybe other people have more numerical examples than that. I mean, you can run the geocoding by itself at the end, so you don't have to run the whole thing again. 0.1, is that a good number?
Yeah, 0.1 is pretty good.
How can we get the name OS, the swaps? The name of the OS, the swaps.
I think they mean the names of the swaths and the orbits.
Oh, swaths and orbits.
So orbits, I think are the main question.
So Catherine wrote a script, since the orbits have always been a problem, because if you download the Sentinel data, it's not hard to find the Sentinel data, but it's sometimes a challenge to get the right orbits because there's Sentinel A and Sentinel B, and they have different times. And so Catherine wrote a script, and I forgot the name of the script, but it's in there.
Yeah, it's download sentinel orbits.csh. I could type it in the chat.
And do you run that in the raw directory? Like you go to the raw directory and then you run it with?
Yeah, wherever your data is stored, you just need the list of the absolute path to your data file.
Okay. And which facility does that go to? Alaska Satellite Facility or the?
It actually goes to ESA because they have a better sort of reach out and get the orbits API.
Okay. And you manually create a file listing the pairs you would like to interfere with after the alignment step then run INTDF tops with just your list? And I think the answer is yes. But, and in fact, if you're willing to spend some time, you could look through that P2P script that runs all the other scripts, and you could make your own version to be more efficient or start in different places. So you can experiment with it. When we go to the batch processing later on this morning, or whatever time it is for you, then you have to look a little bit deeper into these scripts and understand what's going on. So I think the answer is yes. I don't know. Has anybody else done that?
I think that's actually you're referring to an answer to a question, and the question I think was how can you make annual pairs? And so that's, I think the answer really might be to that it depends on basically the data that you select when you go to search for your data in the ASF archive or wherever you're getting it. You just have to select the pairs that are the annual pairs. I think there was an earlier question about that, and that was, you may have been reading a comment that was related.
Yeah. And there's also a script that I don't know much about, but maybe Catherine's used a lot. You give it, if you have a whole set of images, you can say, I want the pairs that have baselines less than, say, 200 meters and time span less than 6 months, and it will only select those pairs.
Yeah, it's really useful. I think it's actually called select pairs. So
okay.
Really handy when you have a lot of data. Here, I'll type that in the chat too.
There's a question about, I think what you're asking is about split spectrum. It's a split beam interferometry, I think. And I think Khan will go into that later on. So hold tight, and you'll hear all about it later.
If it means the MAI, then yes, too. We do have a split aperture program in the distribution, and the upper level script is called MAI processing. It basically calls the split aperture to divide your SLC into two, and then run them each individually, and then do a subtraction of phase inside.
But that's for splitting the spectrum along the azimuth direction, right? For ionospheric correction,
Yes.
and can also do the range split, which
Yeah,
is compute a parameter in the config file.
Yes.
Those are great questions. And I think Catherine's going to go through a similar directory structure for time series. And then you'll see a lot of the same things, but a few new things. So we have more time for questions, but there'll be another opportunity to ask the same kind of questions.
Does anyone know what inverse Insar is?
I have no idea.
I'm not sure what that's referring to.
Maybe solving for a model.
Yeah, like an inversion.
Yeah.
But that's more related to after you get your Insar results.
Well, next we're going to hear from Matt Way about filtering and phase unwrapping. And this is at the heart of a lot of the interferometry, because selecting the right filter and the right phase unwrapping parameters and near neighbor and so on is sometimes a challenge. And then maybe we should ask more questions about which parameters are best. Okay, take it away, Matt.
Hey, can you see the full screen?
Yeah, looks good.
Looks good. Okay. This is Matt Way. I'm an associate professor at the University of Rhode Island. And I've been using GMTSAR for a long time, and Today I will cover phase unwrapping, and the slides were developed by me and Rob Mellers, and mostly, and Rob and I switch each year to talk about this, and also their contributions from other members of the GMTSAR team. The main reason we talk about phase unwrap is Insar measures phase shift, not deformation. Okay, so the this figure is kind of simplified version. If you think about the solid line being the data for the first image, and the dashed line are taken as a repeating image, then Insar measures the phase shift between these two lines. Depends on the location of the pixel in the image, and also the deformation at that location, the phase shift is different. And one thing is phase shift are only within a certain range. Then we have to reconstruct phase shift to, or not reconstruct, maybe convert phase shift to deformation. All right, that's why we talk about phase shift. And phase unwrapping. And here are two examples. On the left is the Ridgecrest earthquake in 2019. And there you see these color bands change from red to blue, and they repeat. Okay, so this is a very typical interferometry you see. And on the right is an example of a volcano, and there are some surface deformation caused by inflation of the magma chamber down below, and this is also wrapped. All right, so these are very common you see on Insar publications. Okay, so the basic, on the right, the figure looks weird. Okay, it looks very strange. Anyway, so on the left, this demonstrates the main concept. Okay, so the top figure, these are wrapped, these are original phase shift we measure with Insar, and then the bottom is the real deformation that we want to measure. Okay, so this process of converting these color bands into deformation, that's called phase unwrapping. Okay, and GMTSAR will do it for you. If you run the examples we give, and in the end look at the final interferometry folder, and there are several files that you should pay attention to. There's the phase.pdf, so that's original phase data in radar coordinates, and then these phase mask ll.png, this is one that is geocoded, so it's in latitude to longitude, and mask means it's being masked based on the correlation, and the bed points are masked out. And then there is a phase field mask ll, so this one is not only masked but also filtered. And then the this one, I think it's not SK, it should be phase mask _RL. So this is the phase, so it's this unwrapped phase, and it's not color band anymore. It's a continuous value from a number to another number. Then there's a line of sight _RL. So this one is convert from phase to deformation. Okay, and the mask is done by using this CORLL, so that's a correlation. So anywhere the correlation is low, we masked out. Okay, so these are the files you should look at, and that's a process how you GMTSAR do it for you. Next, I will talk about why GMTSAR do masking and filtering. Okay, so from a principle, well, in a simple way, phase unwrapping is very straightforward. Okay, so you just connect them together to be a continuous value. But the problem is when you look at the real data, some area, especially if you on water or farmlands, steep terrains, or even forest, there's random phase. And in this image, over in the middle, in the orientation going southeast, so there you see there's a band that kind of have, there's the face looks noisy, and these are water and also farmlands. Okay, so these are the things you will deal with when you look at your data, but this is really depends on the location. Okay, and in addition to these, and also temporal decorrelation is a major reason for phase noise. So when you have two pairs that are separated by several years, then compared to two pairs separated by a few weeks, it's much more noisier. The reason is over time, the surface reflector change depends on the how much it change. Decorrelation will cause different noises. So these are the two reasons we do that. So filter. So here is one example. On the left is original phase, and on the right is a filtered one. And you can see that filtered is much more smoother. It has less noise, and phase unwrapping algorithm can take the filtered version much easier than trying to unwrap the noisy version. Okay, here are two images. It's another example. You can tell which one is filtered, right? It's very easy. It's very obvious. It's the right one, right? Okay, so that's filtering. Another thing you can do is mask out areas that have low coherence. Here is an example is Salton Sea in Southern California. These are all in radar coordinates. So these range and azimuth. And on the left is a correlation map. And you can see there is an area of black. This is a lake. And then we, as in the configure file, we have a default value of 0.1, I think, to filter the phase. So then we apply this mask to the phase filter, then you get the phase filter mask. All right, so that's what you do. All right, so you filter it, you mask it, then you can do phase unwrapping. All right, so then on the red is the unwrapped phase we get. All right, depends on your area and what kind of surface you get. Sometimes it will take a long time to unwrap. Okay, so if you, for example, if you're doing the project where you choose a place where you want to try GMTSAR, but then when you track your processing, you notice that it's kept doing the phase unwrapping step for a long time. That usually caused by that in the images there are large areas of random phase. So staff is very powerful, but it will also struggle. There are a few tips. First, you can try to just just slice out a very small area. And if you're only interested in a small area, for example, the sentinel image is quite large, but if you only care about a small volcano, right, you can just slice out that small area and run phase unwrapping. And the setting to do this, there is a parameter in the config file. You can do that. Okay, but over there you have to set it in radar coordinates. So you need to check your radar, your plots in radar coordinates to figure out which small area to cut to, and then run again. All right, and also there is a default threshold for phase masking. I think it's 0.1, but in some cases, if the image is bad, you might consider increase the threshold. In that case, you'll mask out more points than sometimes this help. All right. So this is some parameter you can tweak regarding masking. So there is a threshold snafu, and then there is threshold geocode. So if you want to change a threshold for phase unwrapping, you should look at changes threshold snafu. Okay, and the region, to cut a small region I mentioned earlier, so there is a parameter called region cut. You can do that, and then there are other parameters you can look into. Right, and also sometimes you can change the filter wavelengths. So there is a parameter in our configure file, you can do that too. All right. Okay. So after phase unwrapping, you want to convert phase to displacement. All right. So the formula we used is listed here, and you need the phase change. That's basically your unwrapping phase. Then, depending on wavelengths of the radar system, then the converted rate is a little different. So I have a question: why we use 4 pi instead of 2 pi? Anyone want to give a guess? You can type in chat. Anyone? All right, there are a few. Okay.
There's an answer, yeah.
Yeah, all right. Okay, yeah, all right. Yeah, I think most are right. Yes, because the signal going back and forth, so it's a two-way travel time, right? So we, in order to get displacement, you divide by 4 pi, right? So here is a real example I did a few years ago, looking at an earthquake in Iran. Okay, on the left is the face. This is original face, unwrapped. Okay, on the right, it's wrapped. Okay, on the right is an unwrapped phase in displacement. There is an error in this image. Can you find it?
I'm trying to count the fringes on the left one. How many? There's like 1, 2, 3, 4, or 5 fringes, maybe.
Yeah.
And
Okay.
increasing range goes from like the purple up through the green to the red. So it's hard to think of these things, but yeah.
So first, the unit is wrong.
Yeah. Okay, that's correct. So the unit is wrong. In the conversion, sometimes it can be confusing, and but I would suggest always count the fringes, because we know each fringe for this is sentinel data. All right, so for sentinel data, each fringe equivalent to half wavelengths. All right, so if the wavelength is 5 centimeters, it should be around, each fringe should be 2.5, 2.5. All right. So if you notice on the right, the line of sight displacement, the unit is in millimeter. So which means the deformation in this figure shows only less than 1 centimeter of deformation. But when you look at the fringes, we know it's much more than that. All right, so I recommend whatever you do, always count fringes and double check units. when you try to do the inversion. All right, so I'll stop here, and we can maybe go through a number of questions.
I see a question here. What are the 3 white circles on the right figure? It's probably the previous.
Oh, these are epicenter. Let's be that epicenters.
There's another question that I don't know exactly the answer to. What is the difference between the snafu threshold and the value of coherence I select for the coherent mask? I mean, as I understand it, maybe I have this wrong. Snafu doesn't apply any coherence threshold until after the unwrapping is done. Is that correct? Maybe someone can help me here.
Yeah, I think snafu is basically computing a cost function used for doing an optimization purpose. I mean, it uses coherence as weights, and it won't really throw any phase out. Actually, the coherence threshold we're putting here is actually a threshold that we throw away phase pixels before putting it into snafu. So basically, I would recommend to use the same throughout the processing. Like, for example, you pick 0.1 for doing the masking, then it might be better to pick 0.1 as well for doing phase unwrapping and geocoding too.
Can we use other unwrapping methods? Yeah, you would have to find a phase unwrapper and sort of build it into your processing scheme.
Yeah, snafu sometimes is really slow. We know that because it's doing a zero norm optimization, which makes it really slow. I think there are also other modes of snafu, like the tile mode, which allows you to divide and then unwrap and piece together later on. You could definitely try it, but for the moment, we only have snafu built into GMTSAR as a default.
Here's a great question for Matt. Why is the displacement on the right not a double couple pattern?
Yeah, it's a thrust faulting earthquake.
Yeah, here's the answer. Is there a method to detect and correct potential unwrapping errors? And I think the answer is yes. Maybe Xiaohua, you spent a lot of time doing this.
The simplest one is just you sum up a bunch of interferograms and see whether there are apparent areas that are having 2 pi jumps. That's the easiest way of doing it, but it kind of requires you to do that manually. There are other methods, like a time series method. You could essentially form all the triangular loops in your stack of interferograms, and then try to solve for like phase unwrapping errors by examining whether there are any residues from those triangular loops. You could put some kind of a constraint to it, like a 1 norm constraint or 0 norm constraint, so that it will produce minimum amount of phase unwrapping errors, so that after that, all the triangular loops in your stack interferogram closes to 0. But the problem is that it's a little bit hard to do this pixel-wise because the minimization takes time. If you have a pretty powerful computer, you can do that pixel by pixel, or if you have not so many pixels to solve, it'll probably work that way, but yeah.
But your original solution was to add up unwrapped interferograms, but always do it in a loop. So you come back to the original interferogram, original SAR image, and it should be 0 or 2n pi, is that right? I mean, it's not.
Yes, it's always 2n pi. What SNAFU does is just adding or subtracting 2n pi's to your phase to make things continuous.
What was geometry? Yeah, oh yeah, Catherine said. I think in SNAFU, you can also change MCS. Try to changing it once. Yeah, there's a lot of parameters. There's a SNAFU config file that we didn't even talk about. And I don't have much experience with that. But it would be a good thing to, there's one thing for earthquakes. If you have a big, if you know you have a discontinuity in the phase due to the rupture of the surface, there's a parameter in the config file called defomax that will tell SNAFU it's okay to have a tear in the phase. And that works pretty well with earthquakes. Although most earthquakes, when you get close to the fault, there's always some kind of unwrapping error. And you might have to just remove those data somehow. When calculating the LOS, does the unwrapped phase have to be in radians? Then I would convert to meters. Yeah, I think that conversion is done. If you look in the geocode script, it takes the unwrapped phase, which is always in radians from SNAFU, and it goes into the PRM file, the parameter file, and finds the wavelength of the radar. And then it forms lambda over 4 pi minus, there's a minus sign we talked about yesterday, and then it converts it to LOS. So that's done automatically in the geocode, I think. I think it's in the geocode. These are great questions, and you really have to experiment, but then it's good to have someone to help answer the question. So run the examples. Okay, if there's no more questions, why don't we do one more presentation and then we'll take a break. How about that? So Kang Wang is going to talk about atmospheric artifacts and how to interpret your interferogram. And I think there's a poll set up. So
it's already set up.
Good.
So should I share my screen?
Yeah.
Good. I'm gonna share my screen here. So hello everyone. My name is Kang Wang from UC Berkeley. And in this presentation, we will be going through some of the common laws in Insar, including tropospheric delay and ionospheric delay. And this slide is made with contributions from a lot of colleagues from, including Catherine, Ram Muller, Dave Sandwan's, Tim Wright, and Tim Wright. And some of the common questions we got asked a lot are, how do I interpret the interferogram? And is that possible to correct for the, or to remove the noise in the interferogram? So that's some of the common questions. So to give you a sense of what the atmospheric delay looks like in Insar, I'd like to launch a poll. Can you see the poll coming up on the screen?
I can see the poll, but it's right on top of the image. I can move it. Yeah.
Yeah, so basically here I showed, I displayed a few interferograms over Southern California, and the question asks you to select which one of the interferograms likely represent the tectonic deformation. Do please answer the poll. I'll count down for another 10 seconds.
Well, yeah, it's only half the people have answered, so let's, yeah. You know, a little time.
Yeah, so I see that most people selected the interferogram 3, and some people may have selected different ones, but later on I'll tell you that it's probably about the time to end the poll. Should I wait or just end? Okay, a few seconds. I don't see the number increasing. Okay, it's still increasing.
Probably the instructors aren't answering because they don't want to bias.
Yeah. So anyway, so probably I'll end up the poll because it's already 2 minutes. So we see that most people selected interferogram 3, which is this interferogram. We see a lot of fringes. And people think this is the tectonic deformation or may have some tectonic deformation. Unfortunately, all those 5 interferograms shown here are mostly due to the atmospheric delay, including tropospheric and ionospheric delays. And it turns out that for the interferogram 1, it's in this interferogram, the fringe, there are only 2 or 3 fringes. That's relatively quiet interferogram in terms of the noise level. And for the interferogram B, this turns out to be that the atmospheric delay is correlated with the topography. So you see some ridges along the mountain range. And for the interferogram 3, that's most people selected as the tectonic deformation one, but unfortunately, most of the fringes here are also due to the tropospheric delay, and similarly for the other 2. And for interferogram 5, interferogram E actually also has some possible contribution from the ionospheric delay. So, yesterday we had seen this equation basically suggests that what Insar measures is a combination of both the known parts and unknown parts. For the orbital and the topographic contribution, that's pretty much known, so you can use a model to remove that. But for the tropospheric delay and ionospheric delay, that's mostly unknown. So we have to be careful when we interpret the interferogram. And of course, what we want to know is the phase change related to the deformation. So the tropospheric delay is caused by the delay when the signal travels through the atmosphere. So you imagine that if the pressure, temperature, or water vapor content in the atmosphere changes between the two times when the images were taken, it will cause a difference in the amount of delay. So that's why you see some fringes due to the tropospheric delay. And this in this slide, it says atmospheric noise is unpredictable. That's for the sometimes it's unpredictable, but some part of the atmospheric delay actually it's a systematic variation. So that's only partially true. So also the signal has to travel through the ionosphere, which spans from about 100 kilometers away above the ground to all the way to 1,000 kilometers. So that's a very thick layer of charged electrons. So that also gets the signal get advanced or delayed. So similar to the tropospheric delay, as long as you have some conditions in the ionosphere can also cause a range delay in the interferogram. So as I just said in the last slide, sometimes the tropospheric delay has some systematic variation. For example, the tropospheric delay tends to correlate with the surface topography. And in this figure, we show that we can see that there's an elevation change. So when you do the Insar, you will see that the path delay seem to mirror the elevation on the first day, on the first position. But see, on the second day, the atmospheric delay is so minimal, is so quiet, and along this range, you probably won't see very much path delay. So when you make an interferogram, you will see, when you subtract the two, you will see some elevation dependent variation in the image. This is called a stratified component of the tropospheric delay. So an example is shown here. So on the top, I think on the top that's the elevation, and in the bottom left panel it shows the observed phase change or range delay. So clearly there's a strong correlation between. So this panel also is a phase delay or range change but it's for different interferogram. In both interferograms, you can see that the observed range delay strongly correlates with the topography. So in this case, one can probably do a regression between the phase and the elevation and to remove that. But we have to be careful because sometimes the expected deformation is also correlated with the deformation. For example, volcanic deformation, the deformation around volcano, we know that sometimes is, most of the deformation occurs at the dome and gets smaller and smaller away from the center. So in this case, if you just remove a linear model, will also remove part of your deformation. So that's for the stratified component. Sometimes the atmospheric delay can be very irregular or turbulent. We call turbulent atmospheric. Basically, as this figure illustrates, you on image 1, you have 2 areas of strong atmospheric delay, but for the rest of the places, it's probably very quiet. And for the second day, you can assume that atmospheric delay on the second image is 0. Then when you do the difference between the 2 images, you see that at some places you have a very high level of noise, but for the rest, it's very quiet. This is most difficult thing to deal with. But luckily we have a method to correct for the tropospheric delay. One method is using the GNSS data products. For example, the zenith total delay derived from the GNSS measurement. And here I show example of an interferogram over the Southern California. It covers the Ridgecrest area. As you can see, this interferogram has a range delay up to more than 15 centimeters from corner to corner. Of course, this cannot be due to the tectonic deformation because this time span is only 6 days. And if you look at the elevation here, looks like there are for some places there's some correlation between observed range delay and the elevation, but not from the image wise, the correspondence is not so clear. Luckily for this area, we have a dense network of continuous GPS measurements from which we have obtained the zenith total delay, which is a product of the tropospheric condition. You can imagine that as kind of water vapor content at each GPS station. So this paper, the paper I refer here, proposed a method to decompose the GPS observed zenith total delay into stratified and turbulent parts. For the stratified part, basically you are looking for the relationship between the phase change and also that the phase change and elevation, and the turbulent part, basically you can interpolate the observed zenith delay from that GPS station to your Insar pixels using a method called inverse distance weighting. You do this iteratively, eventually you will get a separation between the turbulent component and the stratified component. And so, you know, in the end, you sum up the two components together. That's what you get from the GPS model, from the GPS products. You can see that the predicted GPS range delay mimics the overall pattern of the Insar measurement. And here it just shows, you know, more examples over the Southern California. Most of the time, yes, the GPS zenith total delay products can give you a first order correction. And if you look at the RMS or variation of the image before and after the GPS zenith delay correction, you can see that most interferograms indeed have a lower variation after you apply the correction. So that's very encouraging. Unfortunately, GPS network, especially dense GPS networks, are not always available. So for those cases, you know, you will have to use other information. One method is to use the weather model. So here I show an example over the Pakistan, where of course we don't have a lot of GPS data. So here we use the weather model that gives you the precipitation, that gives you the pressure, temperature, and humidity at a coarse grade of the region at every 1 hour. And with that, you can integrate how much the range delay at your Insar image. So on the right, that shows the prediction from that weather model. You can see that for this region, for this particular interferogram, the weather model does a fairly good job to match with what the Insar suggests. So that's also a lot of encouraging method. So for the weather model correction, if I'm interested, Geckos, there's a service called Geckos where you can input your dates of the Insar observation and the area of your study, then it will generate a tropospheric delay using a high resolution weather model. And you wait for a couple of hours, you can download that delay product and apply that to your Insar observation. But I have to warn you that weather model is often a hit and miss. That means that sometimes it can do a very good job, but for a lot of cases, for a lot of times, you probably don't get a good correction. Sometimes it may even make your interferograms worse. So watch out for the correction you are applying. So that's a quick look at the tropospheric delay, and then I have a couple more minutes to show the ionosphere. So ionosphere basically is a shell of electrons that spans from, as I said, from maybe a few tens of kilometers all the way up to 1,000 kilometers, and it's primarily related to the ultraviolet radiation from the sun, and that can also cause a significant range change in your Insar. So one unique feature of the ionospheric delay is that it's frequency dependent or wavelength dependent, as this equation shows that the range delay, the travel time delay due to the ionospheric effect is proportional to the wavelength squared. So that means that for the longer SAR system, longer wavelength SAR system, the effect of the ionospheric delay is stronger than the short wavelength system. And also, as I mentioned, ionospheric delay is related to the sun radiation, the radiation from the sun. So it tends to be latitude dependent, meaning that at close to the equator, you might have stronger ionospheric delay. And also, ionospheric delay has a so-called 11-year solar cycle. So supposing you have one acquisition here, which has a low level of ionospheric delay, but if you make an interferogram with a lot of acquisition, say in this time period, you might have a strong ionospheric delay. So keep this in mind when you make long interferograms. So the ionospheric delay sometimes can be so strong that completely dominant your interferogram, as shown in these two examples. On the left, this is the interferogram of the Nepal, and this is Ionospheric interferogram, which has a relatively longer wavelength. So we see that this from this corner to that corner, the range delay caused by the ionospheric delay can be up to maybe more than a meter. This is for the L band. For the C band, ionospheric delay can also sometimes make a strong effect. For example, this interferogram shows an example covering the Taiwan island. You can see there's also a very dense fringes over the entire image. So it turns out to be also an ionospheric delay. So how do we correct for the ionospheric delay? Similar to the weather model that one uses to correct for the tropospheric delay, we can also use the global TEC model if the TEC model has a good resolution. For example, here it shows that for the Taiwan case, one can use the TEC model to get a reasonable pattern of the fringes for this given interferogram. It already mimics the first order pattern of the interferograms, so that's very encouraging. But the global TEC model is very coarse, meaning that the resolution sometimes may not be sufficient for certain areas. So actually, in this case, they used the local GPS measurements, regional GPS measurements, to interpolate the TEC model into their regional scale. That's why you can get a reasonable estimate of the ionospheric delay for this interferogram. Another very promising and popular method recently developed to correct for the ionospheric delay is called range spectrum. So I probably will go very quickly for this method. So basically, it tends to the method tries to split the range band, the range spectrum, the spectrum along the range into different bands, into different frequencies. As we just saw, the ionospheric delay is frequency dependent, it's dispersive. So by combining the phase change from different subbands, we can get an estimate of the ionospheric delay using equation similar to this. So this turns out to be a very promising and very effective, as shown here. So the top row shows the observed interferograms, and the middle panel shows the estimated ionospheric delay using the range split band method, and the bottom panel shows the corrected interferograms using this method. As you can see, the range split band in all three cases removes most of the long wavelength delays, long wavelength noise related to the ionospheric delay. So that's very promising. And similarly, for the Sentinel-1 example we just saw, it also removes the most of the fringes. What's left is the deformation mostly related to an earthquake that we are interested. So yeah, but for the range split method, range split spectrum method, it requires a relatively wide bandwidth, or if the subsystem has two frequencies in its design, similar to like the LISA, over India has two frequencies. That's great. That's ideal for the ionospheric delay correction. But for the rest of the world, you can also use the range split spectrum method. So hopefully through this presentation, you have get a sense of what the tropospheric delay and the ionospheric delay looks like in your Insar. And the take-home message is that one should always assume that your interferogram has atmospheric delay, and try different methods, see which one removes the loss that you don't want. With that, I will stop here and take questions. Sorry, around 20 minutes.
Oh, that's perfect. there any questions about atmosphere? Oh, I have to scroll down here. Ah, I missed all these. Does ionosphere effect always parallel? Does the ionospheric effect always parallel? Always parallel.
Where's the question?
It's in the chat. You might have to scroll down. There's quite a number of questions, but
Sure. Yeah, I see that some of the questions have been answered by you, so that's great. Yeah, so I just showed some of the methods that I'm being using to correct for the tropospheric delay, including the weather model based and GPS based corrections. That's for individual interferograms. For example, if you get an interferogram for an earthquake or for another event that you are interested, you might try those type of external data to correct for your interferogram. And Katya, I think this afternoon will talk more about the atmospheric delay corrections using a method called Candice or Compson stacking, which takes more data. Basically, it takes advantage of the stacking. When you stack a lot of interferograms, the noise gets reduced. So yeah, so for more information about that, I guess you have to stay to look forward to her talk.
does the order in which the corrections are applied matter? Can I correct first for atmosphere and later for topography?
So that's a good question. So for the topography related, for the topography related correction, nowadays I tend to not use that directly. So I tend to use, if I use the weather model correction, because the weather model is an integration, it's an integration from the elevation at the surface of each Insar pixel to a certain height. So that already has the elevation information in it. So when you compute the tropospheric delay from, say, a weather model, it already has the built-in elevation in that. So most of the time, it should already give you a very good estimate of the elevation-dependent part. So, but if you really want to, remove another model, let's say using a weather model does not do a good job, you still see some elevation dependent, I have to do afterwards probably. I have to first use the weather model or GPS, then install the delay products to correct for the large scale variation, and then regress with, do a regression with the elevation, see how much it can improve. But as I said, the weather model should give you a good correction for the elevation dependent part.
There's one more question: how to retrieve the parameters related to the atmospheric noise for a specific place, time, SAR acquisition. And I don't know.
Oh yeah, so
the geckos.
Yeah, for the geckos, you basically input the range of your study area and also the time of the Insar acquisition. For example, at what time of the day and what dates you are interested. That's enough. It will generate the tropospheric delay for you. But as I mentioned, the geckos uses a weather model called EDWCF high resolution. So that has a temporal resolution of, I think, 6 hours. It's even worse than the ERA5. ERA5 weather model has a temporal resolution of 1 hour. But the spatial resolution is relatively lower than the model used in geckos.
Please explain about the decorrelation effects. There's a question.
Decorrelation?
Maybe that was in that first example where we selected which area was tectonic signal. Maybe there was some area that was decorrelated, or I don't know. Yeah.
Yeah, so I see the next question in the chat that is about the geckos. Geckos Yes, the website asks you to input the time of interest. Basically, that's the time, when the satellite flies by your region. So we know that most of the satellites, Earth observation satellites, are sun-synchronized, meaning that the satellite always flies by the same region at roughly the same time, right? So, for example, it's always 6 a.m. or 7 a.m. or 7:20. Those numbers for different regions that may have different numbers, but you want to input your the time when the satellite is expected to fly over that region.
I see a lot of questions now. They're starting to get into the time series part. So maybe why don't we take a break till 11:30? I know we're a little bit behind schedule, and then we'll talk about time series and SBAS and yeah. Lots of questions about the atmosphere and ionosphere. Almost time to get started. I see a question in the chat, and the timing of that question is perfect because I think that's what Catherine and Katya will talk about, and they sort of have a combined talk talking about batch processing and maybe looking at the files, a tour of the files, but also how you do Insar time series, how you might correct for the atmosphere. And these things are all intertwined, so I'm not quite sure. They'll probably be passing the baton back and forth. But I should also point out that this time series methods have been going on for quite a long time. And I think all the instructors here have experience with time series and have different recipes. So we'll hear about one recipe, but there's a variety of ways of doing it. So I don't know who's going to start off. Is it you, Catherine, or is it?
Yeah.
Okay.
I'll go ahead and share my screen. Make sure this works okay. I'll go ahead and play on this guy. Can you see that okay?
Yeah, looks good.
Awesome.
Yes.
Thanks, guys. Okay, so my name's Catherine Guns, and I'm a postdoc here at Scripps Institution of Oceanography in San Diego. And Katya, who you met yesterday, and I are going to be talking together about batch processing and time series processing. So to give you a little outline of what's about to happen here, I'm first going to start off talking about some batch processing scripts in GMTSAR, sort of what the sort of workflow looks like, what the time series scripts look like, what it goes into each one, and that's going to focus mainly on Sentinel-1 with a couple slides thrown in about some other satellites. And then Katya is going to take the reins and talk about SBAS, time series software, and some of the corrections you can apply to time series, particularly the atmospheric correction. And then I'm going to take the reins back and do a brief demo of what a Sentinel-1 time series directory structure looks like. So really just sort of a show the desktop screen view of what the workflow looks like when you're looking at it in a terminal. Okay, so let's get started with why batch processing. I think a lot of us here know that time series provides us a pretty unique look at a lot of different signals. In particular, time series really let you look at the evolution of a certain signal over time. And an Insar time series is even better than that because you get a spatial evolution over time as well. So this whole time series processing workflow uses an insane amount of data to generate hundreds to thousands of interferograms that allow you to create a time series of displacement in a certain area over a certain time. And as you can see here, this is a little blurry, I apologize, but we can look at a whole bunch of different signals, from earthquakes to hydrology to landslides to glacial flow to volcanoes to even just monitoring infrastructure. So this is a really useful process to get to know. So I'm a visual learner, and so I made workflows that kind of look like this. So just providing some very basic workflow imagery of what we're going to be talking about here. So we're going to start with having our safe files in one place, and that's where you go to ASF or ESA and you go download your data, and then each step following that is essentially comprised of a couple different steps. So if this is about to feel like a fire hose information, that's because it is a fire hose information. There's a lot that goes into this. So if you have any questions at all, please drop them in the chat or drop them in the Slack. We will get to them. The first real step, of course, is getting your data, obtaining that data and obtaining those orbit files and all that supplementary information that you need. And the first big step that you take is you actually have to organize your files together if you need to stitch multiple frames together to make a larger interferogram, that you do that here. And once you have all your data organized just the way you want, you then have to choose a master or reference image. And you have to do that because you need to essentially align all the SAR images in your stack to that one master image to make sure that you can interfere them together without any issues. And from that alignment step, you then calculate your interferograms based on the selection of pairs that you want. You then unwrap your interferograms using Snafu for GMTSAR, but of course there's other softwares to do that. And then once you have unwrapped interferograms, then you can apply different kinds of corrections to those. And after you have your corrected interferograms or whatever interferograms that are unwrapped and ready to go, then you plug them into the sort of the time series processing aspects of things. And that's what Katya will talk about in a little bit. And eventually what we're trying to get to here is displacement grids, so a time series of displacement with a velocity field estimated. And that's what comes out of the SBAS program. Okay, so that's a lot. We're going to break down some of those steps here. So I've covered that in a visual way, but what we're going to talk about specifically in the next couple of minutes is how to organize your data, what you have to do to choose that master image or that reference image, how you actually go about aligning that stack of SAR data, how to form your interferograms, how to unwrap them, and then Katya will take over at that point. And just as a heads up, there are, I think that's been said already, but there's multiple examples on the GMTSAR downloads page of time series data sets. So if you're interested, go check those out. In addition to that, we actually have a step-by-step recipe for creating your own Sentinel-1 time series. So that's also at the same page here. So definitely check that out if you're interested. Okay, so organizing your data. I think all of us sort of understand that we have to go download our data, go download our orbit files, get our DEM, but where do we put it when we're starting to think about hundreds or thousands of interferograms? What we're seeing here are two different suggested directory trees for organizing all that kind of data together. So on the left, we're looking at ERS, NVSAT, or ALOS-1 type structure, where you have your main track upper level directory. Then you have your raw directory where all your data is stored. You have your topo directory where your DEM is stored, and then you'll have your interferogram directory for when you create your interferograms. The same sort of principle is applied over here on the right for Sentinel-1, but of course Sentinel-1 is in TOPS mode. So instead of having just a single interferogram directory, we have F1, F2, F3 for each of the subslots, and each of them have their own raw and interferogram directories. And so when we do time series, as it's sort of been said before, like Catherine told us, when we're looking at just a single pairwise interferogram, you actually have to process each one of those subswaths individually, and then you can merge them at the end. So the same principle applies here. We're just essentially multiplying it by lots more data. So in the vein of organizing your data, you go get your additional DEM, you get your orbit files, and then if you need to trim the area of your data or stitch multiple frames together to make a larger area, you can use organized files tops or organized files tops Linux if you have a Linux machine. But this is the steps that you need to take to make sure all your data is ready to go for the alignment stage. So the next, really the big step that you have to take next is choosing that master image or choosing that reference image. And to do this, we can use the tool preproc batch tops. And this is mainly for Sentinel-1, just to give you a heads up. And so the required input for this is a data.in file, which essentially lists your data and your orbit files together. You can actually create that data with prepdata.csh or use the Linux version if you need it. And then we also input the DEM and the specific mode. So in this particular case, what we want to use preproc batch tops to do is to create a baseline time plot. And so mode 1 will do this for us by pre-processing the stack of SAR data that we give it using the default parameters. And then it'll give us that baseline time plot to choose those master images that we need. So let's go look at one of those. This is a very small example of time series. There's only 3 images in this example, but this is what a baseline time plot looks like. So on the x-axis, guess what? We have time in years. And then on the y-axis, we have perpendicular baseline in meters. And so each one of these scenes is plotted based on what time they were taken and what their perpendicular baseline is. And a good reference image covers, of course, your area of interest, but in particular, it minimizes that perpendicular baseline between the other pairs that you want. So to choose a good master image, what we want is to choose an image in our little cloud of data here that's sort of in the middle of everything else. And so for this small example, we're going to choose this one because it's in between the two other scenes. And so once we've chosen a reference image, then we go ahead and start the alignment process. And this is just another visual of what that looks like. Right now we have our organized data, but they're actually slightly offset from one another. They're not all exactly aligned right now. And we've now just picked our reference image and we're going to align everything to that image so we can then interfere whatever image we want. To do that, we actually go to mode 2 of pre-proc batch tops. So this script is really a workhorse for making sure all of this is pre-processed and aligned properly. But the key step in this mode 2 pre-proc batch tops is that when you take your data.in file to tell the program what your master image is, you have to put the master image at the very top of the list. Otherwise, it'll use whatever's at the top of the list. So you need to remember to do that in order to align it to the image that you've just chosen. But once you do all of that, the output that you get is all the aligned.slc files, and those are what we're going to use to make our interferograms. So we're back to this little example on the right here, and what we've done is drawn 3 lines between these images. And what each of these lines represents is a single pair between 2 images. And so when we make our interferograms, we have to stop and think about what pairs we actually want to connect. And this has come up a lot in the chat so far. And so we've talked about select pairs.csh, and this is a tool that essentially calculates for you which pairs of interferograms fall within given thresholds that you set. So if we wanted, all pairs that were within 50 days of each other and within, 100-meter perpendicular baseline of each other, then you'd give those thresholds to this script, and then the output of that script would be an intif.in file, which would list all the different pairs of that fall into that threshold category. So it's a really useful way to create that intif.in quickly and easily. When you have that intif.in file, you can also add your own pairs if you want longer pairs than what you've originally set. It's really easy to manipulate. So at this point, this is where we have to sort of strategize what kind of interferograms we want to make. So this example is slightly different in that we have a lot more images in it. And we have to ask ourselves, okay, based on our signal or on our study area, what pairs do we actually want to connect? What pairs do we want to interfere? Do we want to interfere sequential interferograms? And that means just making pairs between sequential in time interferograms. So you notice the lines are only drawn between pairs that are right next to each other in time. Or maybe we want to make year-long interferograms because we're interested in looking at an annual signal of some sort, or we only know our study area is correlated in the summertime, so we only want to look at summer interferograms. Or do we want to look at everything? Do we want to just make all the interferograms we can? And this is, again, it's not an easy choice to make because it depends on your study area, it depends on what signal you're interested in, but it's a strategizing process that depends on what you want to get out of it. Okay, so once we've decided what our pairs are going to look like, we actually have to make the interferograms. And to do that, we use intiftops.csh. We give it the pairs list that we just created, and then we give it this infamous batchtops.config file, which Catherine showed us. And so this is the critical config file for all your interferogram processing because it tells the program exactly what parameters to use when it processes them, excuse me. And I will say, I'm not going to go through each one of these, but if you have questions about any of them, these are sort of the main ones you need to pay attention to. Just ask your questions. If you don't have one immediately, you can create one using popconfig.csh, and that'll generate a default one for whatever satellite you're using. And the other thing I wanted to say is that for intiftops, we actually have a parallelized version of that. So if you have the computational capability, you can run this script in parallel and basically run multiple interferograms at one time. But that depends on how many cores your machine has and how efficient it is at processing. So we've talked about for tops mode, you have multiple subswaths. You can just process one subswath, you can process 2, you can process 3. But at the end of running those interferograms, you probably want to merge that data. And so you have an option here to merge those subswaths together to create a single interferogram for a single date. And to do that, you can, if you're working on an individual pair, you can use merge unwrap geocode tops, or if you're working on a whole batch, you can use merge batch to do that. And once you have all your merged interferograms, then you can unwrap and then apply geocoding if you want. So for other satellites that aren't Sentinel, we can use the two scripts that are listed here. So pre-proc batch will give you that baseline table that you need to choose your reference image or your master image and your supermaster image. And then when you're ready to align to that reference image, you can use align batch. I'm most familiar with Sentinel, so some of the other instructors may have to answer questions about other satellites, but please ask questions if you have them. And then once you've essentially processed everything, this is where in your individual interferogram directories, you're going to see the same stuff that Catherine went through. So this is where it starts to look just like pairwise interferograms, except that you have hundreds of them or thousands of them. You have your grid files in netcdf format, you have your _ll.grids if they're geocoded, and then you have your Google Earth files, just like Catherine showed us. And I think now we'll turn it over to Katya, and she'll talk about time series methods.
Before I start, are there any questions for Catherine on the batch processing, not time series? I'll talk about time series and we'll take those later. But any questions for now on what you just saw? If not,
There's been some in the chat, but I think Joa's been answering them. Yeah.
okay, cool. Perfect. All right, well, if there are some at the end, feel free to ask them later on as well. Thank you, Joa, for answering those questions in the chat. So I'm going to talk about time series methods. And as David mentioned, there are many different methods. So, and these are just some of them listed on this slide, but there are many more. So one thing that you could do if you wanted to, if you have, basically this slide answers the question of what to do with your big stack of interferograms that you've just made. So one thing you could do is you could simply average them all together. That's also called stacking, a little bit confusingly enough. So you could just take them all and throw them in a pile and average them together, and you will get a mean line of sight velocity. So you'll get a velocity of how fast the surface is moving over your given period of time. And that's good for some applications, but it is only good for things that are kind of changing in a linear way. But often you want to look at signals that are sort of abrupt, maybe transient. You want to look at signals that are periodic in some way, maybe annual, maybe or periodic in other way. Otherwise, signals that go up and down, perhaps. So that's not going to work for you if you just try to basically average and compute a linear deformation or velocity. There's another method that is called the small baseline subset. And there's a test case for this method available on the GMTSAR website. And this is the method that we're going to focus on because like I said, David already said that there are many methods, but the reason we're going to focus on this one is that this is the one that is incorporated into GMTSAR. So you can do the test case on the website. I think there are several now. There used to be, I think, just one, but now there's more than one. And I will explain more about how this method works. There's a persistence scatter, Insar, PS Insar, or stamps. That one, stamps, is written in MATLAB. You can go and check it out. There's Giant, that's a little bit outdated. Now there's another Python package from the Jet Propulsion Lab called MintPy. So you can go, and that one includes a lot of different possible corrections that you can apply: atmospheric, different kinds of filtering, and a lot of things to play around with. So please go check it out. It's called MintPy. And anyway, but however, we are going to focus on the SBAS method. And if I can ever switch slides, that would be really great. Oh, I can't.
Let me switch it. Yeah.
I'm not driving. Thank you. I forgot. Yeah, so we're going to focus on SBAS because that's the one that we have in the GMTSAR coded up. already. So the way it works is basically you take all of your interferograms that you've calculated, and you throw them into these matrices, and there are several of them. So if you look at the matrices on the top, there's one really big one with ones and zeros, mostly ones and zeros. And that matrix basically describes the time span of your interferograms. So let's say your interferogram spans from January to February. You would put ones in the months that is January and February, and zeros in the rest. If it were January to March, you would put ones for three of the sort of parts of the matrix, pixels in the matrix, and zeros for the rest. So basically, it describes how long your interferogram spans and when the acquisitions occurred, and you will eventually normalize that or multiply that by the time span of the acquisitions to get your incremental changes. But it has another component that you can add to it. You can add a smoothing component. That's all the lambdas in the bottom of that matrix. And you can add another correction for the perpendicular baseline. Sometimes there are errors that result from having incorrect measurements of perpendicular baseline, and you can solve for them if you just throw them into this matrix. Then you have the one with the M's in it, and the M's are basically your incremental range changes that you are later going to kind of accumulate into your time series. And finally, on the other side, you have your data with the D. You have the actual measurements of deformation per each pixel, per each interferogram that you are looking at. So our goal here is to solve for the matrix that has all the M's in it. So you're going to put together a design matrix. You're going to throw all your data into the matrix on the other side, and you're going to solve for the model matrix. Next slide, please. I think that's it for this one. Okay. One thing you could do to make it even better is to consider your coherence. So you can basically tell your design matrix that the pixels that have good coherence are good and should be considered more important, should be weighted more heavily, and the pixels that have low coherence, bad coherence, are bad and should not be taken into consideration as much when you're solving for your deformation. And that's going to be different for all your different interferograms. And that, as you can see, that's a method that was developed and published by Xiaopeng Tong, and he in 2016, and David Schmidt. And you can see the difference between the coherence-based SBAS on the left and the traditional SBAS on the right. These are mean velocities that are computed later on from the time series over a certain period of time. And you can see that it's a lot less noisy if you consider the coherence, which is really nice. So that is an option, I think, that you have in the SBAS implementation that is in GMTSAR. Next slide, please. So before we go into any more details, I want to show you some examples of time series and what they look like and how to interpret them. So this was prepared with the scripts SBAS in GMTSAR. That's just the command SBAS. And it requires a few inputs, and one of the inputs is intif.tab, which is a list of interferograms, orbit numbers, and baselines. There's a scene.tab, which is a list of scenes and day numbers. N is the number of interferograms, S is the number of SAR scenes, and the dimensions of the interferograms. And again, there is an example that walks you through this on the GMTSAR website. So let's take a look at the example on the next slide, or on this side. So it's a little movie that shows you that there is deformation happening in the Coachella Valley. That red is negative displacement, so it's negative line of sight. So it's subsidence. So you could see that over time, a lot of these areas go down quite dramatically in the valley. Next slide, please. And there are several corrections that you might want to apply to your time series without, if you just do your SBAS calculation, your time series will end up being rather noisy. And Kong has already gone into this and told you about all kinds of atmospheric effects. Well, they don't just apply to individual interferograms, they apply to the time series as well. And sometimes you see huge signals that you think are tectonic or that you think are relevant to what you're studying, but they actually are due to some of these effects. So there are several effects and several corrections for them. You have to, once you get to a level that's precise enough, you have to consider solid earth tides and tidal loading. You have to consider the ionosphere, especially when you're working at longer wavelengths, such as L-band. And Kang has already gone through all of this. There are weather models or common scene stacking that you could use for atmospheric noise. There's unwrapping, ambiguity correction, which we have also already talked about. And you can also, if everything else doesn't sort of satisfy you, you can finally correct your remaining long wavelength errors using GNSS data. And this, for sure, everybody has their own tricks for, but you can feel free to ask any of the instructors. I think we've all done this, and everyone has their favorite way of doing this. But it works really well. So what I want to say about the slide is that the ideal thing to do is actually a combination of all of this. It's not, I will focus on one method again, because it is built into GMTSAR, and it was developed by us here at Scripps. But the ideal is to try out everything and to find the best combination that works the best for you. Next slide, I hope. Okay, so as I promised, going to focus on one atmospheric correction. And the reason Kang didn't talk about this is because this is really meant for time series specifically. You cannot apply this to one interferogram. Everything else we've covered, you can use on just one interferogram. This is when you have a lot of data. So similarly to what Kang showed, on the right, there is an interferogram that has lots and lots of signal. If you look at the color bar, it varies between negative and positive 25 millimeters for just, and this is, you have to trust me on this, it's an interferogram over only something like 24 days. And it has these huge signal, 50 millimeters, 5 centimeters, ranging in 5 centimeters over this short period of time. But none of it is actually deformation. This has taken over an area that doesn't deform very much at all. And yet there's all this signal. And all of the signal is really due to the atmosphere. And so we have to correct for it somehow. Otherwise, you will never see the signals that you're trying to measure, which could be several on the order of a couple of millimeters per year. So we have to find a way to correct this. And next slide. So you have lots of options. We've already been through a lot of them. Kang did a great job discussing the weather models, total electron content models for the ionosphere. You can also just do filtering in time or in space or both if you think that you know the characteristics of your atmospheric signal, but oftentimes it's a little bit dangerous to assume those things. You can use topography correlated models that were already discussed. Next slide. And I think this was already discussed as well. You may be lacking some resolution. You may be removing real deformation signals. So here we developed a special kind of, it's also sort of temporal filtering, but it is a little bit more specialized that I'm going to discuss next. Next slide. So our atmospheric correction method that is included in the SBAS script in GMTSAR is the premise is that the interferograms, that the pairs that have a scene in common have the same atmospheric contribution. And so because the weather was the same, and if you look at the little diagram on the bottom left, you'll see, if acquisition 1, 2, and 3, the pairs that share acquisition 2 will have the same contribution from the weather because you're subtracting the deformed interferograms. And so basically, if you subtract the interferogram 2.1 from the interferogram 3.2, you're going to make your atmospheric signal bigger. And you're going to be able to calculate what the atmosphere is doing on that particular date, day 2. Next slide. And so if you kind of expand that to lots and lots of interferograms, let's say you have many pairs, you can take a lot of them and basically focus in on one date and subtract the interferograms from one side of that date from the other side, and you will have a very kind of well-defined atmospheric signal that you'll be studying. If you have constant deformation, again, you might at that point you might as well just kind of average everything together. But you know, you can use more and more interferograms on either side, and that will increase the accuracy of your retrieved atmospheric contribution for the particular date. But if you have nonlinear deformation and if you have irregular acquisitions, you need to be a little more tricky about this. So next slide. And basically, just to show you what atmospheric phase looks like, we did this exercise for ERS 1 and 2 and NVSAT for one of the tracks. Just again to point out that some of the signals are very severe, other scenes are a lot more quiet, so you have to account for both cases. Next slide. So yeah, this was already we discussed as well. Some of the patterns repeat, some of them are correlated with topography, so it makes it hard to predict what the atmosphere is going to look like. Next slide. And this is what happens if you have a whole bunch of interferograms that you calculate atmospheric contributions for. You can also calculate the kind of an RMS estimate of the noise for each date, and this figure again for ERS and NVSAT, you can see the bluish points are the ones that are more quiet, that have less atmospheric noise, and the ones that are red and brown and orange are the ones that have a lot more atmospheric noise. And these are normalized to 10. 10 is just the maximum and 0 is the minimum. Next slide. So the way that we basically iterate through this process is that we first compute the atmospheric contributions that are the strongest, and then we move on to the weaker ones. So we kind of jump around in our interferograms to calculate the atmospheric contribution and use the ones that we've already calculated to fix the subsequent ones. So this is how we validated our approach. We actually used data from GPS, which is very, very good. GPS data are considered kind of the ground truth because they record, there are many stations, especially in California, that record data every second. And based on that, the GPS community is very, very good at making their measurements very accurate. And so we compare Insar data, our Insar time series to GPS measurements. And on the left, you can see the time series that are calculated between for the different GPS points that are shown on the right. There is a reference station, CHLO, and all the other points of reference to that. So the blue dots in the figures are the continuous GPS time series. The black dots are uncorrected Insar time series. So that's just what would happen if you just did SBAS by itself without applying any corrections. And then the red is what happens when we apply the atmospheric correction. And you can see that the black points are really rather scattered. So you can see a general pattern in maybe how the deformation is progressing, but you wouldn't be able to look at any details. Whereas the red points, for the most part, are actually able to kind of recover even some variations that you could see in the GPS. So this is just to show that our method works. And we continue to the next slide. So this is the SBAS script. I already talked about some of the inputs. I will go through quickly some of the parameters that you could choose. Again, please feel free to play around and try your own time series. You can choose smoothing factors, so you can make your time series even smoother by adding extra smoothing. You can choose the number of iterations for the atmospheric correction. So as I said, it's an iterative process, and And the more iterations you do, kind of the better it gets. But after say 3, you will just be taking kind of computing time, and it won't be improving so much anymore. And you can choose 0 to skip the atmospheric correction entirely. The wavelength of the radar wave to compute the deformation, you have to input that. The incidence angle of the radar wave, the range from the radar to the center of interferogram, all of that you can find in the metadata of the interferograms, or just look it up for the satellite that you're using. The RMS of the DEM error, if you want to output the DEM error, you can do that. So sometimes we use old digital elevation models and they change through time, and you can use SBAS to calculate the errors and correct for that. If there are misfits, you can also output the RMS of the misfits. And the outputs are going to look like a bunch of files ending in GRD. So they're going to be disp and then some numbers, .grd, and the numbers are going to be the order of the time series. And there's also going to be a velocity grid, which is going to give you the main velocity over your entire period of time. So there's an example command, and you will see this usage if you just go to your terminal and you just type SBAS. You will see by itself, without any options, it will show you this usage as well, that it can. And again, you can look at the examples and try some of those out for yourself. This can be parallelized with SBAS parallel. I think this is a new feature, which makes it faster if you have the computing resources to run the calculation in parallel. Okay, next slide. So again, let's push play. This is the same method that was used that I just described. On the top left, right, you have time series of deformation that have been corrected for the atmosphere using this method, and on the top, on the bottom right, without any correction. Thank you for that, for the pointing. That's beautiful. So you can see that there's a lot more noise in the bottom right, and a lot of that noise goes away when you correct for the atmospheric contribution. And it allows you to look at your deformation signal more precisely. Okay, and if we continue to the next slide. Yeah, so just to reiterate, this is a snapshot of that same calculation. On the left, you have uncorrected time series. You can compute the atmospheric error for that snapshot. The little blue dot, little blue thing, is actually the deformation at the Cerro Prieto geothermal field. So that's a real tectonic signal. And as you can see in the middle, where we calculate the atmospheric error, it doesn't show up. So that is just pure atmosphere. And on the right, you have just pure deformation without much of the atmosphere. With most of the atmosphere corrected already. Again, another way of validating our methods. So let's continue. This is another example just to show you that we can recover, signals that are time dependent. So on the right, you have, so this is a San Andreas fault. It's plotted a little strange so that to make the San Andreas fault look horizontal, but this is at the Salton Sea. And there was a little event on the fault that was recorded by Insar and other measurements. And it happened basically over a time period of a very short time period of a few days. And you could see from the time series on the right that we were able to capture this event that was rather abrupt. It was not linear. It was not the same as just calculating a linear velocity. So that's just another example of using this method to calculate time series. And if we move on, finally, I would like to mention this, the GPS correction that I was talking about before. Again, if you want to correct your interferograms for really long spatial wavelength effects, maybe sometimes you have a ramp that's due to the ionosphere that gets left uncorrected after the split spectrum, or anything else, maybe an orbital error, lots of things can happen. You can always you can always calculate the velocity over a large area from GNSS if you have access to GNSS in your study area. And you can then remove it from your images and from your time series. And again, there are many different kinds of ways to do this. Everybody has their favorites, but you can check out the Jupyter Notebook example on this link on GitHub. And I want to thank Catherine Guns for the slide. This is her slide, thank you. And the notebook is also hers, so enjoy it. It's a beautiful example. And next slide, I don't know if there's anything else. Oh, this is a picture of ice cream. If you get bored of GMTSAR, you can always try ICE, ISCE, JPL software. But I just put this to torture David because he's always accusing me of being an ICE spy here at GMTSAR. So that's it for me. And I think Catherine wanted to go through a little example of, these are the resources that you could access. There are some downloads, some examples, or some step-by-step recipe for a time series in that PDF. Thank you. And we wanted to give you a quick demo. So Catherine's going to take over again.
Thanks. There were lots of questions, but they're being answered pretty much in the chat, but I think we'll have time after Catherine's. And yeah, I think you are maybe a JPL spy. Or...
Yes, I definitely am. I don't even hide it.
Okay, cool. Well, if we need to keep to time, I can try to keep this brief. This is mainly, basically just wanted to show you guys a quick desktop demo of what like a Sentinel-1 time series directory structure looks like. And so I will try to keep this to like maybe just a couple minutes. I have kind of a lot on the screen here. Up on the top is that same visual I showed before, just like a visual walkthrough. On the left is basically a bunch of notes. This is basically a step-by-step to-do list of what you need to make a time series. It's a little ugly to look at in this form, but this is just FY, this is what we're going to like walk through just a little bit. We're not going to do every single step here, but first things first, what we're seeing here is a directory. This is essentially the same structure we recommended at the beginning for a Sentinel-1 TOPS time series or batch processing. And so you see those F1, F2, F3 directories. We have a merge directory. We have an SBAS directory. And if I move this out of the way, we have a topo directory over here. Because we have so much data, we actually choose to store our data in a separate directory. I'm going to list this. It's going to take a second. Unfortunately, so all these light blue stuff of the cyan color is a link. And we actually keep the data somewhere else because it takes so much space that we just link it to where we need it to be. And let me move this up so I can see it properly. So it's a little hard to look at there, but what we have in here is we have our safe files. So these are our main data files. As you can see, there are a lot of them. And then we store our orbit files in here as well. So those .eof files corresponding to the dates of our Sentinel data. And then what's useful about this directory is that we also have, when we run our organized files tops and it stitches data together, stitches frames together, it actually creates two new directories inside this data directory. And inside those directories are the stitched, clean, ready to go safe file data. So that's what's sitting in here. And if we go back to this main directory that we're pretty familiar with, we got our F1, F2, F3, our merge, our SBAS. If we go to F1, you can see what's in here. All the directories are in blue here because this is a Linux system. And the ones we care most about, of course, are intif-all, where all our interferograms are stored, our topo directory, where our DEM and our topo RA grids are stored, and then our raw directory. So if we go to the raw directory real quick, there's a ton of stuff in here because we've linked some of those data files here to process them using pre-proc batch tops. So the raw folder inside your F1, F2, F3 directories is the main place you're going to do pre-proc batch tops. So this is the place where the room where it happens. And what we end up with and what our main objective is to create in this directory is our SLC files. So because I've already run pre-proc batch tops for a large batch of data, we have all of these aligned SLC files listed here. In addition, we also have the PRM files for all of them and the LED files for all of them. And those are a sort of supplemental secondary files that you're going to need for processing. We go back up one directory. We can go take a look at the interferograms, but in this F1 directory is where we run that intif tops command or that intif tops parallel command. And so we can see we have our intif.in file right here, and that lists all the pairs we're going to run. Just out of curiosity, we can see how many pairs and how many interferograms we've got. So 994. That's a lot. I think we go to the intif all directory. We can see all the interferograms listed here. So this is where we start to overlap with what Catherine was showing us earlier. If we just go to one of these directories, we can see exactly what we saw before. So we've got our amplitude grids, we have our correlation grids, we have our phase grids and our phase filter grids, and then we have some of those supplemental files over here. And so this looks just like it does for a pairwise processing, but we just have lots of them. So again, this is our batch processing style we've got going on here. And so we go back up to F1. And one thing I wanted to mention in here is that we also have our batch config file. And so this file is kind of necessary to have basically all over the place, but you need to make sure it's basically the same file everywhere you have it. Because if you change one processing parameter in F1, you need to also change it in F2 and F3 and in the merge directory. So you need to just be cautious of where you have your batch config and what version of it you have. We go back to this guy, we can go to the merge directory, and this is where we keep all the interferograms where things have been merged together. And so it's the same sort of situation where if we CD into one of these interferogram directories, we have some of the merge log information that happened when we merged these files together. But we also have our phase filter grid, we have our correlation grid, and because I've already run unwrapping here, we have all the unwrapping files here. You'll notice that I don't have any geocoded or KML or Google Earth files in here, and that's mainly just to save space, because when you have so many interferograms, you need to save as much space as you can on your computer. But one could absolutely compute that as a next step using your batch config file. And that's unwrapping. It's in this particular location, once you've unwrapped everything, that you would apply any kind of corrections that you want. Mainly for our purposes, we often apply the GNSS correction at this time. So we apply that to our unwrapped interferogram, and we do that here. And then if we go back to this area, we can go to our SBAS directory. And you can see that I've already done an SBAS run here. And so we can see just the files that Katya was telling us about, where we have this displacement grid file, and this is the date of that displacement grid in year and day of year. And then we have, this is the file that gets created from the atmospheric correction. And so you have one for every date. And then we also have our VEL grid, and I've also geocoded a version of it here. So that's what gets output when you run your SBAS. And just to, as an example of what Katya was just saying, if we wanted to look at the inputs for SBAS, we can just type SBAS in there. You'll see the long amount of input information, but this is also really useful because there's a lot of different sort of choices you can make about how to run SBAS. But it's that simple just to pull up that information. And I think with that, I'll go ahead and call it. But if there's any particular questions about structure or anything like that, I'm happy to take them. I'll go ahead and stop sharing. Are there any burning questions, or has everyone answered all of them?
Great, thanks. There have been questions going on in the chat, but I imagine, I think once you start doing the time series, you're going to have lots of questions.
Yes, definitely.
Yeah, it's just, a lot of it's just dealing with lots and lots of data files and big disk space.
Yeah.
That was great, thanks. Actually, I learned a lot there because I haven't done a time series in a long time, and so now I can see all the details that go into it. Wow, it's pretty complicated.
it's complicated but possible. You know, it's just a matter of bookkeeping and making sure you've got all your options set. And if you make an error, go back and make sure you debug correctly and everything. So, but if there's any future questions, if you start your own time series, I'm happy to take questions in the future too. So, FYI.
Vertical displacement from SBAS. Can I get vertical?
So SBAS, yeah. Oh, go ahead. No.
No. You know, we're getting 2 line of sight displacement time series, and we need 3 to get the vertical. So you can do things like subtract a model horizontal, but there's no way to uniquely get the vertical out of it.
NICER's gonna help.
Yeah, with the left looking, yes.
Yeah.
One thing that happens too, that I know Java gets emails, they'll run SBAS and then all of a sudden it just crashes. Doesn't, you know, it says, I forget what the error message is, but it's because you've run out of memory in your computer. Because if you take those 1,000 interferograms that Catherine had, and then you multiply that by, say, 2,000 or 3,000 by 3,000 in each one, and then times a correlation and a phase, and it starts to fill up your memory. Like easily get 100 gigabytes, you need 100 gigabytes of memory. So there's a new option in SBAS to use memory mapping to the disk, and that'll solve the problem. So it'll use the disk as your memory, but it will take very long to run. So there's not really a good solution for that. Okay. Well,
Maybe only use the sequential interferograms could be one option.
yeah, you could just use sequential, or you could filter them more so the size of each file is smaller. Usually you don't want to get time series with 100-meter spatial resolution over all of California. It's just way too much data. So you might want to dumb it down to maybe 500 meters or even a kilometer, at least for testing. And then if you really want some high resolution, you could cut the area down and do a SBAS in a much smaller area. A lot of different strategies. Okay. Okay, let's move on to applications. And then in your breakout sessions, I think those of you that are trying time series will have lots of questions. So have to ask the instructors. So we have Jiapeng Tong here from Beijing, and he's going to talk about volcanoes. And Jiapeng, it's like the middle of the night still there. If you're still on the line, that's great. But do you want me to share my screen with the PDF file, or do you think it'll work from your computer?
It will work for my computer. I have a PDF. I have the point.
Okay, great. And Jiapeng was actually the one that started the time series with ALOS data a while back, and doing all the alignment. So a lot of that comes from Jiapeng's early work there. Yeah, go ahead, Jiapeng. Okay, we don't see the screen yet. But if you want, I can do it.
I think he's gotten kicked out. He's
Oh,
been
really?
having problems staying on.
Yeah, I know. The connection's not great. Yeah.
I don't see that he's actually on the call now anymore.
Okay, why don't we move on, and then if he gets back online, we can jump in and do volcanoes. But the order of these applications doesn't really matter. So, Kang, are you ready to present something, and then?
Oh yeah, I can go ahead and let Jiapeng jump in afterwards.
Okay.
Hello?
Oh, yeah, okay. So
Right.
I just stopped. I'm gonna stop sharing, and Sharpen, maybe you can go ahead, take over.
My internet connection is not very good now. Sometimes it locks me off, so I'm sorry if there's any problems.
You want me to share my screen with the volcanoes on it? Maybe it'll help. Or you can do it, either way. Uh-oh. I think we lost him again. I see the box, but I don't. Okay, he's probably having trouble. Okay, I think he got bumped out again.
I see him on here. He's just having
Okay.
problems with sound.
There he is. Okay,
Okay, I'm sorry.
let me share my screen because it'll take less. Oh, you got it. Go ahead. Yes.
Okay, you got it?
Yep. No, you
So-
have it right there. Perfect.
Okay, let's start. I will talk to you about applying Insar to study volcanoes.
Uh-oh.
Now he dropped.
Uh-oh. Let's try one more time and then we can move on to Kang. We did get a slide this time, so that's good. Oh, that's fun. I'll send him a message.
Well, now he's back
Okay,
on.
I'm back online.
Okay.
Can you hear? Can you
Yes, we
hear
can
me?
hear you now. Yeah.
David, why don't you go ahead and share his slides, and that might help with the bandwidth.
Sure. Okay. Share screen. Right there. Okay, nice. It would, yeah, this was adapted. I don't have the recent slides, but if you should be able to see it, Japan.
Yes, I can see it. Okay. So today I will talk to you about applying Insar to study volcanoes. Next slide, please. So why monitor volcanoes with Insar? There are basically two perspectives. First is from hazard perspective. So we want to assess changes and potentially hazardous developments of volcanoes. For example, there are possible precursors for upcoming eruptions. So if there is any changes that can be detected by the Insar, we will So we want to understand dynamics of volcanoes, eruptions, and deep magma flow. So we will use models to model the surface deformation we observed and try to understand the sources that is in subsurface. So there are several advantages of using Insar. First of all, it's a remote sensing technique. It can monitor volcanoes at a low risk and low cost. So we don't need to install any instruments near the volcanoes because that will be very dangerous and high cost. Because Insar is a spatial, very spatial, high spatial resolution, but GPS is a low spatial resolution, but a high temporal resolution. That so Insar and GPS are very complementary to each other. And lastly, we want to so usually we want to look at slow continuous deformation using Insar. And because volcanoes are very active and dynamic, usually volcanoes doesn't deform at a constant rate. So time series are very useful. Next slide.
Whoops. It's not a, here, there it goes. Got it.
Okay, let's look at our first example. It's in Galapagos Islands. So on the right here, you see a big picture of Galapagos Island imaged by Insar. So all the colored images are interferograms, and it's color coded by the displacements. So we see there are a lot of things going on. For example, there is a uplift and there is a subsidence near the volcanoes. So there are several types of volcano activities. First, there is a dark intrusion, and second, there is a magma chamber inflation and deflation. Third, there are level flow cooling. So all these three volcano activities can cause surface deformation that are measurable by Insar. And if we look at the figure on the left, we see a model that try to understand the surface deformation. And so we model the interferograms with the Morgan source. Morgan source is a simple model of surface inflation from a subsurface pond source. So we can model it with the Morgan model, but the residues are very big compared to a SEAL model that's shown in the lower panel. We see that the SEAL model performs better in matching the interferograms. Okay, now we can look at another example in Hawaii. That's this is our work done by David, and this is the interferogram in 2007 from May to June, and these interferograms have captured a large deformation from volcanoes, and the right here shows you uplift. The purple color shows you subsidence. So we found that there is a big signal from subsurface dark injection. And so in the middle, there is a rifting and flank uplift. And then on the surrounding areas, there is a deflation of Kilauea volcanoes. And there is also some decoration from surface changes. Next slide, please. Okay, here we're looking at the same region, but with GPS data. So the GPS vectors plotted in red. So all the vectors pointing to the source means that there is a big movement, big scale movement of the ground. They all move to the source. They all move to the source, and it turns out that there is a basal slip event that occurred along with the intrusion. So the combination of GPS Insar provide us some new results. So next slide, please. Okay, so before we can look at volcanoes, individual volcanoes, with Insar, we can also study regional volcano activities. So this is an example from Andes. It shows you that we can monitor volcanoes in a regional scale. So Andes is in South America. Here, the Nazca plate is subducting beneath the South American plate, and it caused the widespread volcanisms. There are 1,000 volcanoes that are less than 20 million years old. So these are very young volcanoes. And there are 53 volcanoes that are potentially active. And from the results here, we can see many activities like inflation and deflation and they all start from different time. The color shows you a 5 centimeter displacement of one fringe. So there are a lot of deformation that are on the order of centimeters. Next slide.
Oh, we may have lost Japang again. So Melissa suggested, actually, this is about halfway through. Here he comes. Okay.
Oh, okay. I'm sorry,
Right.
I'm back.
Yeah.
Okay.
If we get cut out again, you could record this and we could put it on the site, but keep going, please.
Okay. So let's look at another example in alluvial trench. Here we can study the hazard posed by Okmulgee volcano. The Okmulgee volcano is located near the alluvial trench, and the picture here shows you an interferogram made from NVSat 2003 to 2004. And this interferograms has shown several fringes near the center of the crater, and from counting fringes, we can see that there are about 10 centimeters of deformation, and we know that there are multiple repeated eruptions in the last 100 years, and it poses hazard to nearby communities as well as commercial jet between North America and Asia. Because of the volcano ash, it can be very hazardous to aircraft. And so the surface deformation may provide clues to subsurface magma movement and possibly impeding risk. Next slide, please. Hello?
Yeah,
okay.
it takes a minute, yeah.
Okay, so here we can look at atmospheric effects, which was talked about by Kang and Katya before. So when we interpret interferograms, it is cautious to separate atmospheric effects from deformation, but sometimes it's very hard to separate those two. So for example, in the figure left here shows you a simple model where you can have a different stratified water vapor from 2 days, and by subtracting these two water vapor contributions, we can have a similar we can have a cyclic deformation pattern that look like a real deformation, but actually it's not. It is caused by stratified water vapor near a volcano. And on the figure to the right shows you the atmospheric model. From this model, we can predict how much signal we can see from interferograms. And the model, the atmospheric signal is very close to the observed Insar signal. And this shows you that the atmospheric noise can be very similar to real deformation. And we should be cautious to interpret deformation signals like that. Next slide, please. Okay, next we can look at the real science problem. So we can look at the monitoring of 2018 Hawaii eruptions from Insar, and this work has been contributed by many people here, listed in the slides here. And so we are using Sentinel-1 data, and we are looking at 2018 Kilauea volcano earthquake sequence. So we will be using Insar GPS time series to understand deformation and erupted volumes. Next slide, please. And so Sentinel data have very good characteristics. First of all, it's free and open, and so everybody can get that data. And then it has very small baseline, so very good for time series analysis. It also has accurate orbits and frequent acquisitions and a long mission lifetime. So we follow a standard processing procedure with GMTSAR. First of all, we can do the geometric alignment, and then we choose the primary seed and many aligned secondaries, and we use amplitude dispersion to weight the interferogram before filtering, and then we calculate the baseline, short baseline interferograms, and then we use SNIFU to unwrap and mask out the water regions. And then we correct interferograms using available GPS data. Finally, we use SBAS to generate time series. Next slide, please. So there's a sequence of events that occurred during this volcano eruption. So it's a very complicated sequence of events. In April 30, the lava in secondary vent began to drain, and May 2nd, the lava in main vent began to drain. May 2nd to 4th, the east rift zone begins to open. On May 4th, the venting begins at La Lini Estate. May 4th, there is a magnitude at 6.9 earthquake occurred on a low angle thrust fault, and so on. There's a lot of activities that going on in this region, and we try to separate them from Insar. Next slide, please. So, okay, here shows you an example or a result of the Insar time series analysis. This figure shows you the descending time series from March to September. The oceans are masked and replaced with nearest neighbor. Unwrapping is done with SNIFU, and for each interferograms, we force it to match GPS. And this result shows you a big subsidence signal that occurred, and it has complicated temporal evolution. Next slide, please. Okay, we can then make profiles of the displacement field, and we can look at these profiles. So there are 3 profiles that made. First, the AA prime shows you a profile that across the summit, and the colored coded lines are the displacement, cumulative displacement that are occurring from March to August. We can see that the summit has subsided by 1.5 meters during this eruption. And
Oh, shit. So cool.
Yeah, and then there's also very large subsidence near the other 2 profiles. Okay, next slide, please. Okay, and then we want to model it with a multi-source. So the figure on the left shows you the results. So from the figure, you can see a very detailed subsurface multi-source model. There is a big decrease in volume at the depth of 1.5 kilometers, and then below that, there is some volume that is increasing. So from this model, we can calculate how much volume has been lost during the eruption. So the volume change from the multi-source shows you, but they're about 0.25 kilometer cube of volume loss. And also there's a LiDAR and a UAV results shows you a different volume change. 0.07 kilometer cube. And then we can ask, how does this compare with the volume erupted along the lower southeast rift zone? And it turns out that if the discharge rate is 100 meter
All right, we may have lost him.
I think it's
Hello?
sound. There we go.
Okay.
hello,
great.
hello.
Sometimes there's a delay, but it's okay now. Yep.
Okay, okay, that's good. Next slide, please. Next slide, please.
Okay.
Okay. Here shows you another type of volcanoes. It's called mud volcanoes. So this volcanoes is made of mud instead of rocks. So the mud volcanoes is in Azerbaijan. Okay, and it shows the interferogram shows you some uplift and subsidence signal that that occurred along with the eruption. This result is from Rob Miller's. Okay, next slide, please. Okay, now to summarize, Insar is very useful for volcano monitoring, and we need to be careful with the atmospheric corrections. And then Sentinel data has been a very significant improvement to other old satellites, and Insar can be combined with the GPS or other data, and that will be very powerful tool to study. Okay, that's the end of my talk. Thank you for listening.
Great, thanks. I'm sorry for all the cutouts, and thanks for staying up in the middle of the night in Beijing, because I know it's early morning there now.
Oh yeah, I also learned a lot.
Yeah, thanks for coming.
Yeah.
Let's see, we're gonna ask, oh yeah, the only question is if you had got cut out completely, we're gonna have to record it, but I think that worked pretty well. So there were a few hiccups, so.
Okay.
Are there
Yes.
questions for Japang or either about this or the time series? He's a time series expert too, so. I don't see any in the chat. So Japang, are you meeting with your students? I guess on
Thursday.
Thursday. Good. All right.
Yes. Yes. We had a meeting before, and now we can meet again on Thursday.
Okay, great. And
yeah,
you pick a better time to meet with them than the middle of the night. So yeah.
Yes.
Okay. Well, thanks.
Okay. Thank you.
So Kang is up next. We're going to talk. We're a little bit behind schedule, but I think, if it's okay with everyone, if we finish by 1:30 or so, I think, that's fine. If people can hang in there. Kang is going to talk next about earthquakes and post-seismic, and he really has interesting results on post-seismic stuff. So I think it's worth waiting.
Okay, thanks. Yeah, so hopefully I can speed up a little bit to save some time for the rest of the speakers. Yeah, so maybe at this point, you probably have seen a lot of applications of Insar in different areas, but I think the first application of using Insar to study the ground movement was probably the in the 1992 Landers earthquake in Southern California. And since then, the application has really opened up. It's been applied to so many areas, which you will see in the following up talks, as well as the one you just saw from Xiaopeng's presentation. So I think in the beginning, the Insar, this is the image of the post-seismic interferogram of the ERS1 ERS1 using ERS1 data. And back then, I think the setup was not specifically designed for Insar. Correct me if I'm wrong, Dave, but I think it was not because this paper called it that as an opportunistic science. And nowadays, with the new satellite missions that are specifically designed for interferometry and ground movement measurement, it's becoming a routinely performed task, and it's been getting so much powerful. And actually, in the perspective of earthquakes, in the field of earthquakes, actually, nowadays we can routinely measure the surface deformation of any continental earthquakes of above maybe magnitude 5.5 or slightly higher, magnitude 6. And we can do that very quickly thanks to the rapid access and open data policy of recent missions like Sentinel-1. So here is the screenshot of a Twitter from a colleague who's doing who's regularly modeling the surface deformation due to earthquakes around the globe. So here you can see that the earthquake occurred. This is an earthquake in Afghanistan recently, which killed more than 1,000 people. The earthquake occurred on June 21st, and the first post-seismic image was available on June 29th, and we already got a model 2 days after. Actually, we were able to get a model in maybe a few hours after the satellite flew by, but this is an example to show you that how quickly we can model the surface deformation related to earthquakes. So with the surface deformation measured by Insar, how can we answer the questions related to the earthquakes? Of course, we can using the data to derive a detailed and high resolution map of the surface deformation, as shown in this figure, that uses the ERS data from both ascending and descending tracks, combining with the azimuth, the pixel offset measurement along the azimuth direction. We can actually derive the three-dimensional components of the surface deformation of this earthquakes, of this earthquake. And using the surface deformation shown here, one can derive the sleep model to understand what happened beneath the Earth's surface during an earthquake. Here it shows the sleep model for the Landers earthquake. Is this Landers or Heckman? I forgot. But anyway, so this is probably the Heckman earthquake. I think so. So, in this type of figure, the color generally represents the amount of slip, and the vector represents the direction that the fault is moving on one side with respect to the other. So, this is a very routine done task nowadays for moderate to large earthquakes. And that's for, generally those type of earthquakes, earthquake model assume the Earth is elastic, meaning that, everything will reset to the status before the earthquake. So if you were to if we're going to measure displacement, measure the displacement at a point close to the fault, you will see that the displacement increases with time and then offset by the earthquake. However, what we often see in reality is that right after the earthquake, there was a short time period during which the velocity, the surface deformation velocity is higher than the rate before the earthquake. And for this type of periods, we call it post-seismic deformation occurred in this time period. We give a special term called post-seismic deformation. So that's what I have been looking at in the past several years. So there are several mechanisms that can give rise to the post-seismic deformation following large earthquakes. As illustrated in this Christmas tree-like diagram, the strength of the rock increases with depths in the crust. So when it reaches a certain depth, the temperature and the pressure become so high so that the rock will deform ductilely. So under sudden stress change, the material will start to behave in a ductile fashion. This is so-called viscoelasticization. It generally occurs in the lower crust or upper mantle. And the other commonly observed post-seismic process is called afterstep. It's basically a continuation of the fault motion after the event, after the earthquake. And the third commonly observed post-seismic deformation has something to do with the fluid in the crust, the movement of fluid in the crust, because the Earth's crust has pore space, so the fluid inside the pore space will respond to the pore pressure caused by the earthquake. So after the earthquake, the fluid has to migrate from the high pressure region to the lower pressure region. So that causes surface deformation as well, and the corresponding surface deformation is called a pore elastic rebound. As one can imagine from this type of figure, post-seismic deformation provides us important insight into the mechanical properties of the Earth's crust. For example, the deformation related to the viscoelasticization can be used to probe the rheological properties, specifically the viscosity of the lower crust and upper mantle. And for the deformation related to pore elastic rebound, one can use that to infer the hydrological properties like the hydraulic diffusivity of the Earth's crust. And lastly, afterstep, can be used to study the frictional properties on the fault. So here is an example of post-seismic deformation following the 2015 Gorkha earthquake in Nepal. So this earthquake caused a lot of fatalities, as you know. That's a magnitude 7.8, and the black contours in this figure represents the co-seismic state model that we derived. And on this figure, the color represents the post-seismic deformation. You see, so here's the inside represents the post-seismic measurement. So the color represents the post-seismic deformation occurred about 1.5 years after the earthquake. As you can see that the region beneath the co-seismic down dip tip continues to move at a relatively high rate. So after 1.5 years, the cumulative post-seismic deformation has been up to a few centimeters in this case. And by the way, I should mention that for this case, we used the persistent scatter analysis for this region because of the thick snow and tough terrain. The traditional insights, it's pretty challenging. So we used the Sentinel-1 persistent scatters to extract the good pixels and do the time series analysis. Yes, using the measurements, we can derive a after-state model for this earthquake. The reason we started with after-state because actually we started with other mechanisms that, as I just showed before, like viscoelasticization and the pore elastic rebound, but none of them works. None of them can feed the data except after-state. So that the indication is that the post-seismic deformation that we saw from the inside is primarily due to after-state. So the natural thing to do is to model how much the steep has moved, how much the fault has moved after the earthquake, and where the steep distribution is located. So here's the after-state model we got, and we see that about 1 year after the earthquake, the down dip part of the fault continued to move by amount of about 300 millimeters or so. And strikingly, there's very little or no steep to the shallow part of the fault, indicating that this fault, the main Himalaya thrust in central Nepal is still locked at the shallow portion. The next example is a post-seismic deformation following the 2017 earthquake that struck the border between Iran and Iraq. Similarly, the black contour represents the post-seismic slip model, and the color here represents the cumulative post-seismic deformation derived from 1701 Insar. As you can see, in this case, actually, we can derive very lines temperatures using the Compson stacking method to correct for the the atmospheric delay, as you just saw in Katya's example, and we can even retrieve the decaying feature of the post-seismic deformation very nicely. So using similarly for the earthquake, the deformation one year after the earthquake is dominated by after steps, so we can model the distribution. We see that for this event, it's pretty interesting that nearly all the after step occurs either up dip or down dip of the post-seismic rupture. There is nothing, almost nothing happening right beneath the post-seismic rupture or in a region that ruptured during the earthquake. So that's a pretty striking feature. And this this kinematic inversion result seems to be fairly consistent with what one would expect from a velocity strengthening frictional model, a numerical simulation, assuming that the after step is driven by the rate strengthening friction on the fault. So this is the kinematic inversion, and this is a numerical simulation. They seem to match with each other pretty well, to the first order at least. So lastly, I would like to show an example of post-seismic deformation that is likely caused by poor elastic rebound. This is a map of the post-seismic deformation following the Ridgecrest earthquake, and this is the vertical component obtained by decomposing the downside deformation from both ascending and descending tracks. Of course, there are some assumptions that we made during this exercise, but anyway, this is a good representation of the vertical deformation field. We can see that close to the main shock epicenter, there's the zone of uplift. The color, the warm color, positive color represents uplift. So this area is uplifting by about a few centimeters after the earthquake. Similarly for this area, and we think that the deformation here and the uplift here, the uplift in this region here and here, as well as the vertical deformation around the fault tips, has to do with the poor elastic rebound, has to be caused by the poor elastic rebound. Because if you think, after slip to cause opposite sign of motion around the fault tips, and the other mechanism, viscoelastic relaxation would produce much longer wavelength deformation. So specifically, we think that the vertical deformation we saw after the Ridgecrest earthquake was primarily due to poor elastic rebound. And in this case, that's also mechanically consistent with what one would expect, because you can see that the fault here changes track to form a releasing band. So during the post-seismic rupture, the pore pressure in this area drops. So after the earthquake, the water will migrate from the higher pressure region to this area to produce uplift. Similarly, one can analyze the deformation in this region. So this is mechanically consistent with what the poor elastic rebound model suggests. And in this study, we're actually using the surface deformation temperatures at the location that is likely due to poor elastic rebound to estimate the hydrological diffusivity. And we found that the data seems to be consistent with a model that requires a diffusivity on the order of 0.01 meters squared per second for at least for this area. So the last example, what I just showed was my own studies. Of course, there are other studies to to explore different properties of the Earth's lithosphere using post-seismic deformation. One, of course, is to look at the rheological structure of the lithosphere. Here, I show that the several studies using the Insar to look at the post-seismic deformation following large earthquakes in central Tibet, and to estimate specifically, they were interested to look at the dynamic diffusivity, effective viscosity of the lower crust and the upper mantle. And lastly, there was also another mechanism called fault zone collapse, which is also observed by Insar. So this is the other post-seismic relaxation mechanism in addition to the three that I just showed earlier. So this mechanism, is caused by the fault zone recovery. Basically, we think that the fault zone might be damaged, so it expands a little bit during the earthquake phase. So after the earthquake, the fault zone might collapse a little bit to produce surface subsidence. And this is a nice example of this type of phenomena after the bomb earthquake. So we see that from the I think this is bomb earthquake. It must be ERS. I forgot, maybe it's ERS. So we see that from the study found clear evidence of surface subsidence right along the fault, right along the rupture zone after the earthquake. So this is called fault zone collapse. So with that, I will conclude. So Insar is an important tool to study the earthquake and the post-seismic deformation at very high spatial and temporal resolutions, especially with the current SAR missions. And the dense catalog of Insar provides us unprecedented opportunities to study the fault zone rheology. And also, as I mentioned, the new satellite missions has a wide coverage and a short revisit time that allows us to map the deformation associated with earthquakes very rapidly after the earthquake. That's it, and I'll stop here and take any questions if you have.
Great, thanks. Are there any questions for Kang? I don't see any in the, oh, here it is. Here's a question. Is it expected to have 3 possible relaxations for any earthquake? How much time?
Yeah, so that's a great question. Yes, actually, that's the challenge of the post-seismic studies. Most of the time, the 3 mechanisms are coupled together. But what I just, in the example that I showed, fortunately, one of the mechanisms dominated the deformation, so we can, treat deformation as just one mechanism. But for the Ridgecrest earthquake that I just showed in the last, the majority of the deformation is actually due to afterstep from Insar. I just showed you the vertical component, but horizontal component of that has to be due to the afterstep, and we got a reasonable afterstep model from that. And also the Ridgecrest, in the Ridgecrest area, we had the good coverage of GPS data. We can see that the far field deformation, is more consistent with visco relaxation. How much time after the earthquake? Generally, it depends on the magnitude. So you can imagine the larger the earthquake is, generally the time, the longer the expected time could be to have observable post-seismic deformation. But of course, it also depends on the rheological properties of the lithosphere and the fault zone. For example, if the viscosity is very low, it may decay very fast. So you might have you have to action very quick after the earthquake. But for high viscosity lithosphere, the deformation can last much longer. And similarly for afterstep and the visco and porous rebound, the deformation duration really depends on the mechanical properties of the corresponding source.
Great.
So for, yeah.
Go ahead.
Yeah, so I see there's another question. Oh yes, the deformation pattern of the three mechanism are different, right? Yes, for thrust event, generally the deformation due to afterslip and say viscoelectrification is quite different for deep slip events. That's why we chose the Nepal Nagorka earthquake as a starting example. So in that event, we can easily distinguish the mechanisms of different the deformation pattern of different mechanisms. But for strike slip events, it can be a little bit challenging. Yeah, is there a lower magnitude threshold to observe the core and the post-seismic deformation? As I briefly mentioned, now this magnitude generally for continental earthquake in the crust, we can probably see the deformation, co-seismic deformation for earthquakes above magnitude 6. That's probably a conservative estimate. People have seen deformation from even magnitude 4, magnitude 5 point something, but there was an earthquake in France that was a very special earthquake. The magnitude was only 4 point something, but it ruptured to the surface, so it had a lot of surface deformation and afterslip as well. Yeah, so some earthquakes have a lot of clear post-seismic deformation, some may not. So it really depends on the mechanical properties of the lithosphere and the fault. So that for that question is probably difficult to answer. Thank you for your questions and enjoy the rest of the talks.
Thanks. That was interesting. So next we're going to hear about hydrology and crustal fluids, and I should tell a little story. Yuri Fialko and I would teach an Insar class, and everyone wanted to make an interferogram and look at earthquakes and volcanoes, and they mainly saw hydrological processes. And now that's become sort of the mainstream use of Insar. So Wes Neely is going to tell us about it. We had some old slides, but he's working with a new group of researchers on this. So take it away, Wes.
All right, thanks. Hi, yeah, I'm Wes. I'm a postdoc at Stanford. I did my PhD down at Scripps, and I took this very course, what was it, maybe 5-6 years ago or something like that. Though I never got my certification signed, so I don't know if it actually counts.
It's in the mail.
Yeah, it's in the mail. Hopefully I can share my screen. Yeah, I should be able to. Okay. All right, and everyone can see this? Great. Yeah, so I'll talk a little bit about how we can use Insar for understanding various hydrological processes and crustal fluids. A lot of this is going to be related to groundwater, because that's kind of where my home is. But I'll briefly go over kind of the mechanisms for the types of deformation we observe. We'll look into the urban and agricultural subsidence, how we can use this to understand potential groundwater dynamics, processes related to subsidence and uplift related to hydrocarbon production, geothermal energy, and then a little bit about elastic loading and unloading, which is it's mainly been used in GPS, but increasingly I think there's potential for Insar. Okay, so how does the Earth deform related to changes in things like crustal fluids or hydrology? So one of the big ways is through this poroelastic response. So if you think about your aquifer system, and you have the saturated saturated Earth. If you zoom in, you can see these gray little lenses would be your minerals. This could be a clay or something like that. The water is sitting in these pores, and it's acting as a pressure pushing, supporting the granular structure of the of this aquifer system, and it's helping push it apart. So if you extract groundwater, you reduce the pressure of the system, and these tend to collapse on each other, and that manifests as subsidence. Certain materials behave a little bit more differently, where they, if you if you take water out and then you put it back in, it will actually uplift. But for clays and silts, it's really hard to regain that structure you once had. So oftentimes the subsidence you observe in clays is permanent. And if, through time, a time series might look like, a long-term trend of subsidence that's modulated by kind of a seasonal oscillation, with the just natural wet and dry periods during the year. The other way is through this kind of idea of elastic loading. So if you put a lot of mass at one location, it's going to deflect the crust, and you can measure that deflection, and you can actually estimate how much mass was added or removed based on that change in deflection. And so, I often think of this kind of like, the space-time theory of relativity, where you have a larger mass has greater deflection than these smaller masses. And if you really, really want a simple way to think about it, you can think about it as like a house of cards and a trampoline. So, once the cards kind of fall and they get in this more preferential orientation, it's hard to, force them back out into a different structure. Oftentimes people will say a sponge, but I actually like house of cards a little bit more. And then of course, trampoline, if you have a heavier person standing on it, they're going to be, deflecting that plane downwards more than if you have a lighter person. So over recent years, we've seen a lot of subsidence around cities, and this has to do with growing populations. To the left, this is Las Vegas, so an area in the desert. Probably a city shouldn't exist here, but people want to live here, and if there's no surface water, they rely on groundwater, and this can lead to large subsidence. So this is kind of an interesting color scale here. It's not wrapped. It's just a cyclic color scale, but it's showing upwards of 20 meters of subsidence. And other areas like Mexico City over here on the right, it's subsiding at times upwards of 2.5 centimeters a month. So I think there's estimates now that's it's closer to like 50 centimeters a year, something like that, which is absolutely wild, particularly from an infrastructure standpoint. Sorry, let me just move that up. And for just an example, I believe this is a well. It looks like it might be a fire hydrant. I'm not sure. One that was installed back in presumably the early 1900s and 1930s. And I think this is 2013 now, but there's been upwards of 8 meters of subsidence. And, that makes that kind of unusable. There's a lot of infrastructure damage in terms of cracking. You can see this building is kind of slumping off to one side. So it's quite important for just, Insar has been this really amazing tool to really understand the spatial extent of the subsidence related to groundwater pumping. This is even more problematic around coastal cities. So these major urban population centers right on the ocean, you have relative sea level rise just from changes in climate, the melting glaciers and ice sheets, and it's exacerbated by subsidence related to, again, most likely groundwater pumping. So these areas that are already threatened by flooding are threatened even more due to these changes in groundwater. And Insar is a great way to resolve this. And I was trying to find a good example of this, but there's after major storm events such as like Hurricane Harvey, there's been some studies that have actually used the Insar coherence to map the flood-prone regions. So if you look at this panel right here, I think this is a FEMA model of where they expected flooding to occur. And then if you look at this bottom panel, where it's blue is where flooding actually occurred. So the FEMA did capture the field model did capture where flooding was, but it also missed out on a lot of regions that that they, that ended up flooding. So this is, Insar shows it's another way to assess these flooding risks, to have flood risk assessments. And cities aren't the only places using groundwater. We also see large groundwater uses in agricultural regions. So this is the San Joaquin Valley in California. So the Central Valley, LA would be down here somewhere. San Francisco Bay would be up here. And this is a region that is sinking upwards of 35 centimeters a year over the last couple decades. The Western US has been undergoing these persistent and intense droughts, and that's really shifting a motivation towards using groundwater because surface water, it's just not as available. And but I will say, even in a wet year, 40% of the water demand does come from groundwater, but in a dry year, that can be upwards of 70%. And it's with Insar, we really have this great spatial mapping of it. We also have the temporal evolution of the subsidence. So we can just kind of watch this march through where it should cycle through, because this is only 2015 to 2017. So after October, it should go back. And so yeah, we see which areas are developing or are sinking faster than others. We can see how different climatic or how different weather events, or how different years, some years are wetter than others, how this spatial and temporal evolution changes due to available water. And one of the big things within agriculture, which I'll just kind of briefly mention, we've touched upon throughout the previous lectures, have been this issue of decorrelation. So, oftentimes the fields that were, these fields, there's agriculture is covering a lot of this area. Those fields, you harvest, you change the scattering properties so much that the images are no longer coherent, but you oftentimes have the places in between the fields that you can use that are stable and have high coherence. So I don't, this can have some problems with your unwrapping if this is the case, but there is signal available. So this is in Colorado. These circular fields are not as common in California. So California, there's a lot of roads and various things that cut across through or a lot of infrastructure that go through the road, the fields that we can use. And using Insar, we can also estimate various parameters about the groundwater system. So we can understand things about the total storage change. We can understand potentially what's the hydraulic conductivity of these systems, the storativity, things like that. And this is some work that I've done using that same time series that I showed before. We can model that time series as just a linear rate or a sinusoid, and we can start to understand more and more about that system rather than just what is the long-term velocity. So, just fitting a sinusoid to this, we can estimate these parameters of the seasonal amplitude, and also the seasonal or the time shift. And so you can think of this time shift as the timing of peak uplift. So this is for the water year 2017. It was a very wet year. We see regions, I did not include the scale bars on these, but we do see regions here where this bright yellow is places that are oscillating upwards of 6 centimeters a year. So up like peak to trough, this is a region that would move 6 meters up and down, which is quite interesting because sometimes where you have these strong seasonal components, you may not actually observe a long-term trend. So in terms of what are the local stress changes occurring. You might not get that from these from the velocity map, but you can get that from the time series. And then we can see how does that timing evolve. How does that evolve through time in terms of when is the peak uplift. So this, you might be able to interpret it as whenever there is a peak, you have your most amount of groundwater, you have recharge or something like that. That's when the ground surface would be at its highest during your time period. And then when you have your intense pumping in the summer months and whatnot, that's where it might be the lowest. So this map might demonstrate this a little bit better, this movie, where we can see the regions that are moving up first. So we'll just start. Here's January. This is a place that's uplifting and it's progressing with time. You can see it's kind of migrating along these rivers. So we actually think this might be a recharge location where you have water infiltrating, and then the pressure response due to that infiltration is kind of radiating outwards and into the valley. And so we can actually use that to potentially understand things about groundwater recharge and flow, which is kind of a new thing, but it's really, really exciting. And a lot of the groundwater managers have a lot of interest in this, particularly for knowing, where and when water is coming, where it's flowing, how should they communicate with each other. So a lot on the horizon with Insar understanding groundwater dynamics. Now I'm going to switch gears a little bit and go talk a ton about the use of it for another subsurface fluid, hydrocarbons. So Insar is really, really well poised for mapping where oil and gas production is occurring. So this image right here you can actually see it. I'll just skip back up a little bit. It's actually in this map. It's this kind of string right there. This is Lost Hills, near Lost Hills. This maps perfectly to where this kind of lighter area. This is, if I were to zoom in on it, you would just see thousands upon thousands of oil rigs just moving up and down, pumping. And we can observe subsidence of, 20 centimeters a year in these regions. Off north of Bakersfield, California, there's another oil and gas field. And the subsidence is actually, it's really well bounded by some mapped faults. So it's quite interesting how these changes in subsurface fluids elicit a observable surface deformation that also agrees with the underlying geological structure. So it's quite cool. The first time I saw this, I was like, oh, that's weird. There must have been an unwrapping error. But then it turned out, nope, it was just bounded by a fault. Then this is a region, the Delaware Basin, kind of in West Texas, New Mexico. And again, Insar is used where we can map the locations of production, then also injection. So this is a very useful tool for kind of understanding, what are the effects of wastewater injection and extraction, and various things like that. So very, very important. You really would want to know, you would want to know about this, all this subsidence, especially if you have oil and gas infrastructure. So if you have pipelines moving through, it would be problematic if it was over an area that was sinking, several centimeters a year. We can also use it to, Katya actually showed a nice video of this, of some work that they did, Eric and her did, looking at the Cerro Prieto geothermal field. And, similarly, these fields, they're extracting hot pressurized water from down deep that then gets converted into steam to turn the turbines that create energy. So, and then that leftover water and condensed steam can be re-injected. So the INSAR again is really well. It's really great for observing a whole host of different types of subsurface features, and it can be quite important if you're trying to consider the local tectonics. So this occurs right at a step over. So changes in these in hydrology, and they could potentially modulate the stress field and potentially affect the earthquake cycles. And then I think this is actually my last slide. I'm trying to make it a little bit quick, but I mentioned that elastic loading and unloading. So this is kind of different than that poroelastic effect. So where the poroelastic, when you took water out or a fluid out, the ground would sink. And if you put water in or fluid in, it would uplift. This works in the kind of the opposite way. So if you take water out, it would uplift. And if you were to load the ground with some sort of mass, weight, or fluid, water, whatever, then the ground would sink. So so this is an example. This is using GPS. It's basically you can weigh how much change there's been in mass, and this is all of it's related to reductions in the snowpack over the Sierra Nevada. And it's the same type of observation and measurement that INSAR can provide in terms of a surface displacement. So you can actually use it for, you could use it over here, but it would take a lot of INSAR to cover a region this large. But you could look at, isolated regions such as a lake, such as Lake Mead. What we're seeing here is this is actually a time when the lake was filling up, and we can see subsidence, ringing around this lake related to increases in the lake level. So this is what that plot is showing. This this dotted line is the lake level, it's the water level in the lake, and then this solid line is the observed ground motion. So you can see as the water level goes up, line of sight, and in this case, the line of sight is increasing, which means it's moving away from the satellite, so it's subsiding. And so with that, I mean, that's just a preview of everything, or a preview of some of the things you can do with the with INSAR. By no means is it everything, but I'm happy to try to answer any questions that might be on the chat at this point.
Great, thanks. Don't see any questions right now. I'm always impressed by the coastal land subsidence being sometimes much larger than sea level rise. So when people talk a lot about sea level rise, they sometimes forget that in a big city, it's the subsidence that is going to get you more than the sea level. But
yeah, absolutely. I mean, like sea level rise is what, like 2 millimeters a year or something like that.
Yeah.
And this is showing almost, an order, or it's about an order of magnitude more, sometimes even more than that. So it's, it can be quite problematic.
Yeah. Exactly. Okay, here's a question. Whoops.
Oh, I just closed it. Oh, well.
Let's see.
Oh,
wow. These questions are, I have to attend another meeting. Oh, that was, I don't know what happened. My chat is going crazy up and down, but do I see any new questions?
Okay, how do we quantify errors of an interferogram after doing all the correction? That looks like, particularly for scenarios like subsidence where motion is usually small in comparison to an earthquake. Oh, okay, yeah. So I believe this question is related to, like, when you have these very compact features, how can you be confident that what you're seeing is subsidence versus maybe an atmospheric effect? Would that be kind of, that might be related to a bit of it. So one of the things, you know, when we talked about the atmospheric correction is that when you look at your pairs or your, you know, in time, the your time series set, the atmosphere is, it'll flip signs depending on whether or not, you know, one side to the other. So usually with these subsidence features, they don't flip sign oftentimes. They're usually pretty strong going down. So, you know, from one interferogram to the next, it'll be continually going down. Whereas if it's just an atmospheric artifact, then it tends to switch signs, depending on where, you know, which scene is being differenced, or with the order of differencing occurring. But then quantifying the errors, it's a hard thing to do. I mean, some of you may be better at actually knowing how to do this. A lot of people assess it against GPS, GNSS. If you're fortunate and you have one in an area that is sinking, if you have extensometer data for a place with you know, it's you know, like in your subsidence pool, that's another way that you could assess how well are you capturing all the subsidence from Insar versus what's actually measured.
I think the next question is more on post-seismic, so I think that's
yeah,
a different topic. And I think we should move on to interseismic, but one question I have about interseismic and hydrology is, in California, we have both going on at the same time, and we have it both affecting GPS and Insar, and how are we going to separate them? And I don't have an answer, but I throw that out there.
Yeah, I mean, your signal is my noise and vice versa. So
yeah, too many processes.
Yeah, for a lot of it, I mean, where the regions that I've been, you know, that I've kind of shown here, they've been quite dominant. You know, they're more of a dominant signal. So I kind of ignore a lot of the horizontal motion. I've used the SCEC geodetic model in Southern California to remove the horizontal estimate of displacement, but it's probably not it's not an ideal way. It'd be nice to use just Insar on its own to separate these.
Yeah. Okay, well, let's move on to interseismic because we're a little behind schedule, but Eric Lindsay agreed to talk about interseismic processes, and so take it away, Eric.
All right. Yeah, thanks a lot to everybody for sticking around. I know it's gotten a bit after time, but I'm excited to be here to talk to you about this. This is the last lecture for today, is that right? So I'm going to talk about interseismic deformation. And, you know, typically when we think about interseismic deformation, what we're thinking about is that slow pattern, that slow process of crustal deformation that happens in between earthquakes in a tectonically active area. So we're thinking about, here's an example for a strike slip fault. The velocity across that fault is sort of a slow gradient. And then when the earthquake happens, obviously you get deformation just catching up that deficit, so that the long term over time is that geologic offset on a fault. So for interseismic deformation, what we're thinking about is this sort of slow pattern. And we're thinking about rates of millimeters a year to kind of at most centimeters a year. So we're really thinking about the smallest signals. And these are really kind of always something of a challenge to figure out and how to observe them. And of course, our big problem, as everyone has talked about, and especially Katya has talked about, the atmospheric delays. So, you know, this is that same example showing an area that, you know, might not be deforming very much, but you have something like 4 centimeters of atmospheric noise. And so that's much, much larger than your tectonic signal. So this is always our challenge. And kind of the first approach that was developed to deal with this is just stacking. So I think Katya mentioned this also. If you just add up a whole bunch of interferograms, sometimes you can beat down that atmospheric noise because the noise tends to be random and uncorrelated. So over time, if you add up enough, you'll get kind of magnify the signal and decrease the noise. So this is an example from a paper, now about 15 years ago, that had stacked together 35 interferograms. So when you're thinking about stacking, I thought it would be interesting to make a comparison between stacking and time series. So we want to think about how do we do the stacking, and what really is the criteria that goes into that, and how can we optimize that. So a question for you all to think about: what would be the difference between the interferogram formed from time A to time C versus if we added together the interferogram AB plus BC? So I'll just let you think about that for a minute. Think about what Wes was talking about and what Katya was talking about, how we can kind of, the atmospheric noise present on day B is going to have the opposite sign from interferogram AB and interferogram BC. So if you just write that out, there's really no difference. So the interferogram AB is really formed by date B minus date A, and then CB is date C minus date B. So that means that this B actually cancels out. So you're just left with C minus A, which is just interferogram AC. So that's kind of an interesting observation. So this is actually should be true anytime you're doing Insar, is that if you have these triangles, you should observe sort of no difference between the ones kind of the two-step interferogram versus the one-step. There can be some caveats to this related to your filtering. Your filtering can introduce some small sort of noise in that, so you can't always exactly trust this. But in general, this is going to be the case. So if we're thinking about how to stack up all these interferograms, we could form our interferogram AC, and then we could form AB and BD and DE. But if we think about whether should we include AB or not, in this case, if we include it, what's happening is we're canceling out the atmospheric noise of date B, but we're essentially doubling the atmospheric noise of date A if we include this interferogram in our stack. So what we would really want to do is know whether A or B is has more atmospheric noise, and then we would only include this one if date A is less noisy than date B. So here's kind of an example of that. Using that method that Katya talked about, so we can estimate the level of noise on any of the particular days, and then we can form our stack based on sort of connecting up those images with less noise. So you can see I've sort of left out some of the scenes there that are in red or green because they have higher noise than the blue. And in particular, what we should really think about is trying to get our end dates to have low noise. So this is the result of that, and it seemed to work pretty well in this case. So this is two different, an ascending and a descending track from NVSAT. And so we kind of carefully chose the interferograms in order to optimize the atmospheric noise reduction of the stack. And it actually worked pretty well. So, but of course, when you do a stack, you're not getting the full time series information, you're just getting the velocity. So, you're losing some detail of your information. But if you're really just interested in that slow, long-term process, this might actually be an okay choice for how to do your processing. So I thought I would kind of ask the question, which is better, stacking or time series? So here's an example. I just made up some synthetic data where I've got a time series. It's got 5 years of data with about 150 images. So this is sort of mimicking like a sentinel frame sort of data-wise. And I've added sort of 1 unit of noise, and the rate is also 1. So these are sort of fake units, but we've got pretty high noise level. So what we can do, if we just fit a line to that time series, we're able to reconstruct the velocity pretty accurately. But I thought it would be kind of fun to compare what does it look like if we make a stack. So the first thing that you might try if you're doing stacking is you just form all your nearest neighbor interferograms and maybe the next pair. So sort of stack nearest two interferograms. And what we find is this is actually significantly worse than just doing the time series. So if you can only afford to make your nearest two interferograms, the stacking is not a good idea. Really, you need to do the time series to get a more accurate measure. So I've sort of generated 1,000 sets of synthetic noise and then run this calculation each time. And you can see that for the time series, we have an uncertainty of about 5% of the velocity for this level of noise that I've added. But for this stack, we're getting about 4 times higher noise. So that's really not a good sign. So one thing that people often do is include yearly interferograms. So if we add in those year-long time span, then we can see this is actually getting quite a bit better for our stack, but it's still worse than the time series. So what if we just included all possible interferograms? So now there's 11,000 interferograms. Luckily, this is synthetic, so I didn't have to calculate it for real. This would probably take you weeks of computational time. It turns out that if you make all possible interferograms, then your stacking results are identical to the time series. So I was pretty surprised by this. I might assign this as a homework for my students to ask them to prove why this is the case. But it's kind of an interesting result. So then the last thing is related to what we were talking about earlier. If we had some information about the noise on each of our dates, and then we could just exclude the noisy dates from the stack. So if we do something like this, this turns out this actually works pretty well, and we can do slightly better than the time series. But this is kind of an unfair comparison because we're comparing it to the time series that didn't have any atmospheric noise reduction. So, really, if you were applying your atmospheric corrections to your time series as well, you probably would do just about as well as this. So, so my conclusion from this is basically time series are sort of the way to go. As long as you're applying your atmospheric corrections to your time series, you're probably getting about the most accurate velocity that you can. So, and in addition, if you do your time series, you're also able to detect whether things are not deforming linearly, which you might be interested in. So, generally, I would say at this point, you probably always want to do time series and not stacking. Although it's nice to know that stacking is kind of available, but if you need to do that, you probably want to be really careful about the dates that you're choosing and the pairs you're making. So, so thinking about what noise level or what level of accuracy can we expect to get, this is sort of based on the time series analysis. If we had 6 years of data, we should be able to get better than 1 millimeter a year uncertainty. This is sort of estimated for, kind of realistic estimates of the level of tropospheric noise for Sentinel data. So, Sentinel has now been operating for more than 6 years, so we really should be able to measure these interseismic velocities at pretty good levels of accuracy. But there's always some trouble. And one of the troubles is that the atmospheric noise is spatially correlated. So you've kind of seen these patterns, and we can actually quantify this with a sort of an autocorrelation measure of how spatially correlated the atmospheric noise is. Tends to be correlated at distances of sort of tens of kilometers. So that means that over a distance beyond 20 kilometers, you're getting kind of the maximum level of atmospheric noise. So if you're looking at a small feature like fault creep or some of the smaller features that Wes was showing, you may have actually lower noise than kind of this worst case, because the atmospheric noise over that distance is smooth. But for tectonic velocities, we're often interested in the really long wavelengths, and there we may be sensitive to atmospheric noise over these long wavelengths and also ionospheric noise. So it's still really a challenge, despite the fact that we have so many years of data. It's always a real challenge to get accurate long wavelength information. And you can see this. So this is, one kind of estimate of how you would, if you combined just a couple of GPS stations with your INSAR, these are estimates of the noise coming from different contributions. So the bottom two in particular, you can really see how the estimated uncertainty kind of increases with distance from your GPS station that you're using as your reference point. And this sort of makes sense because of that sort of spatially correlated noise. So if you're looking at over small distances, if you have a reference point, you can get pretty accurate information, but over larger distances, it's going to get more and more difficult. So one thing that people do to try to overcome this is use GPS to fit the long wavelengths. So here's a recent paper from the North Anatolian Fault in Turkey, and what they've done is they projected the GPS. So you can see the GPS data set down in the lower left here, and they've projected each one of these velocities into the line of sight for both the descending and the ascending, and then they fit a plane across that each one of those frames, and they can remove the plane that represents sort of the long wavelength error in the INSAR and force that plane to agree with the GPS. So that's one way to kind of remove your long wavelength errors that you have in INSAR. And you can see that, in this case, for across one of these profiles, they've done a pretty good job. The GPS projected into the same line of sight as the radar looks pretty good. And one thing that they did that was kind of neat that we've talked about a little bit here is if you have two line of sight directions, then we don't have full 3D information, but if we know something about the direction, we can estimate any other sort of two components of velocities, assuming that the third is 0. So in this case, what they've done is this is the east-west velocities, and they're assuming that the north-south component of the motion is 0. So this might not be exactly true for this area along the whole fault, but it's reasonably good. So you can see that they've kind of separated out that east-west component from the vertical component by just sort of adding and subtracting those the ascending and the descending frames. And we actually did this for this area for the San Andreas Fault as well. So we have this is the ascending image here, and then we have the descending image. And so what we did is actually we assumed that the fault, the horizontal motion is moving in the direction parallel to the San Andreas Fault. So we can separate the fault parallel motion from the vertical motion. And so you can see this actually worked pretty well in this case. So in the first, the top two images, you see a lot of these sort of really sharp, bright features that look a bit strange, kind of in different areas around the Coachella Valley. And you see that they mostly go away in the fault parallel motion, and they're really present in the vertical. So we really succeeded by knowing something about the azimuth of the tectonic motion. We can separate that tectonic motion from the vertical motion. If you have even more GPS, you can do an even more advanced thing, which is you can project your line of sight, or you can project your GPS into the line of sight everywhere, and you can be very specific. So this is a case where they've actually combined several frames, and so for each one of the frames, the line of sight is going to be slightly different at every point. And so they've projected the GPS into the line of sight after interpolating it to make a smooth map of the deformation. And then when you can essentially do a kind of a filtering combination. So this is actually something you can do in GMT with this GPS gritter function. So you can interpolate your GPS and project it into the line of sight, and then use that to control the long wavelength deformation. So it's, this is something that you always have to be a little bit careful when you're doing this kind of thing, because you're throwing away some of the information from the INSAR and deciding to trust the GPS entirely. So if your GPS is wrong, or if you made a mistake, you could end up with wrong results also being propagated into your INSAR. So, another approach that people have tried is to just simply not use any GPS information at all and just try to compare at the very end sort of the Insar result and the GPS result and see how similar they are. So that's kind of another approach that is sort of maintaining the independence of the two data sets. But it's really sort of a philosophical difference whether you want to just make the best possible combination or whether you want to keep them separate as much as possible. So just kind of thinking about that, the spatially correlated atmospheric noise is our biggest challenge. Things like ionosphere are particularly bad when we're talking about long wavelengths of deformation that we're interested in. The ionosphere could look just like a real tectonic signal. So stacking can work in some cases, but really, I think my suggestion to you all is really stick to time series, and then you fit the velocity to that. And if you're adding atmospheric corrections to that, you're probably getting kind of the best possible velocity that you can measure. And GPS GNSS observations can help to sort of constrain those long wavelengths, either sort of a plane or an interpolated ramp. And uncertainties better than 1 millimeter a year should be possible, but it's obviously not guaranteed in all cases. So you're going to have to sort of try out for your own case and see how it works. And then, so lastly, I wanted to mention a little bit about WinSAR. This is sort of my last chance to talk to you all. So WinSAR stands for Western North America Interferometric Synthetic Aperture Radar Consortium. Although we're thinking about changing the name to mean the W should mean worldwide, since we're no longer really just Western North American. There's about 300 institutional members, and we have access. If you're a member, joining WinSAR is free. You just have to apply on our website, and it gives you access to this data set that includes some ERS and ENVISAT, as well as RadarSat, and other sort of data sets that have been acquired mostly over Western North America. It also gives you sort of access to host your own ALOS-2 or TerraSAR-X data. If you're a user who has gotten access through proposals to those space agencies, we'll host that data for you, and then you can just keep it there since it's such large data. And we provide sort of like authenticated access to that. And finally, the thing I wanted to advertise a lot is you can upload your own data products and get a DOI for them. So we have this page here, and you can upload and fill out this request to DOI. It hasn't been used a lot. We've got sort of about 100 interferograms that people have uploaded. We're kind of in the process of upgrading this system. So hopefully by next year, that'll be really a good functional system that we'll start to build momentum on this being a place where people put their final time series and interferograms whenever they're publishing results. So, our goal is that this will be a place where if you want to say, okay, Wes just showed me some amazing time series Insar over the Central Valley. I don't really want to have to process that all myself, but what if I could just go and download it and try it out? And maybe there's other people who've processed the same area in their own way, in their own strategies, and then I can compare them and stuff like that. So that's our goal. It's not really there yet, but hopefully that's the direction that we're moving. And I would really love to have all your support in uploading your products there. After you've taken this class and what you've learned, you can start to share your results with us. So thanks a lot.
Thanks, Eric. I see a couple questions in the chat. But again, we should be uploading our intermediate results because it's hard to process these data. So
Yeah.
The first question I see, it's from Kang, and it says, in the synthetic tests of stacking, did you use only those good interferograms or all?
So in the last one that I showed that was slightly better than the time series, what I did was I made nearest to and also yearly interferograms, but I excluded any dates that had noise larger than 1 sigma of the the noise level that I had added. So it was kind of a synthetic case where I knew the exact noise level and I could just remove the noisy dates.
Yeah, that's what I mean, because for the stacking of the real data, you have excluded the localization dates where the noise is high. So I thought maybe in the synthetic test you should also discard those bad dates.
Yeah. So that's what I did that for the stack, but I didn't exclude the bad dates for the time series. So I think that it ends up being a little bit of an optimistic. It's making the stacking appear better than it really is. So if I had also excluded those noisy dates from the time series, then the time series would have been less noisy than the stack. So yeah, so my main conclusion is stacking is not really as good as time series. I hope that makes sense.
So I have a question about Sentinel. In January, we lost Sentinel 1B. So we had regular acquisitions every 6 days, and now it's gone to every 12 days. And how is that going to affect the time series? I guess we'd have to run some synthetic cases or.
So it's going to get harder to do things like the common scene stacking because those rely on having a lot of kind of nearby in time acquisitions to really help the stacking result be better for the atmospheric noise removal. As far as uncertainties on time series, it's similar to a GPS time series. Really, the most important thing is just the length of the total observation. So having less images is not such a big detriment. It's as long as Sentinel-1A keeps going and they eventually launch Sentinel-1C, they're going to keep getting better and better.
Yeah, it makes sense. So are there any more questions? Oh, wait.
Is there a possibility to remove the stripes among results of different frames and tracks? Do you mean in the case?
That I think the stripes he meant were those California ones, and actually those stripes are expected because the look angle changed from near vertical to more horizontal, like you sweep across the scene. So they shouldn't match at the edges. It's a little weird. Yeah.
So these stripes, this is real. This is not an error. This is because the line of sight is different between the two frames.
Exactly. Yeah. And we should see that in the data too. Yeah.
And
So
one way of helping that mitigate this kind of problem is that maybe in the future, if you have enough data, you can do a decomposition to get the individual east, north, and those ones. If the data is getting better, you would get rid of some of these discontinuities, like what is shown there. Yeah.
Here you can see where they've got enough data, like in this blue box. They can estimate the east-west, but then over here, they don't have both ascending and descending, so they can't accurately estimate the east-west.
Oh, here's a good question. Is it critical that GPS and Insar cover the same time period to be integrated or not? Or what if they have different sampling in time, like the Insar has every 12 days and the GPS is continuous? And
so if you believe that you're looking at interseismic deformation that's constant over time, then the time span of the GPS is not so important. But if you're if you think that there's some temporal deviation, then you would want to be real careful about your comparison and your corrections. So there's another question: which data source can be handled easily by GMTSAR regarding NVSAT data, WinSAR or ESA? I think they're in the same format. I can't remember what the format of NVSAT data is, but I think you should get the same format.
The older NVSAT format, but there's also I think the newer format. I don't remember exactly, but I think both of them could be handled by GMTSAR.
Yeah, one is unfocused, the other is focused to SOC, so both can be done with GMTSAR.
So here's a great question. Are we going to show any glacier examples? And we should, but we didn't. So maybe one of the students could have you can run these things over ice. Sometimes the motions are too rapid, so things decorrelate. And and also you don't always have a good topographic model, but really that's a great application. Well, it's getting late and I'm supposed to be in a meeting at 2. So thanks everyone for hanging in there. Thanks all the speakers. Sorry we're so late, Eric and Wes, but I think most of the people stayed on, and we'll look forward to seeing everyone on Friday at 10 for student presentations. Maybe we'll see a glacier one. So.
Thanks a lot. Hope to see my group on Thursday. And the rest of you all